Hello there, and welcome to Life Beyond Seen, where curiosity drifts slower than the tide and science takes its time to wander beneath the surface. Tonight, we're not looking up at the stars or across the vastness of time. We're going down, far below the reach of sunlight, into a place so deep and so hidden that even the ocean itself seems to hesitate before descending there. The Sunda Trench. A name that sounds quiet and unassuming, like a line drawn in the sand, but in truth, it marks one of the most dramatic boundaries on our planet. A place where the Earth folds in on itself, where continents slide beneath the sea, and where the pressure of existence is measured not in hours or days, but in tons pressing on every square inch. Before we go any deeper, I'd love to know, where are you listening from tonight? Somewhere near the sea, perhaps? Or maybe in the middle of a city far from the sound of waves, where the hum of traffic has replaced the ocean's rhythm. Wherever you are, it's strange to think that beneath your feet, no matter how far inland, there's still an unbroken chain of rock connecting you to the floor of the Indian Ocean. Every continent, every island, every mountain, all stitched together in the slow, unstoppable fabric of Earth's crust. And far to the east of the Indian Ocean, that fabric dives downward into darkness, swallowed by the Sunda Trench. If you find this kind of slow journey soothing, maybe give this video a like or subscribe so more wandering minds can find their way here. It helps this small corner of calm reach others who might need a place to let their thoughts drift quietly for a while. Now take a slow breath and imagine the ocean stretching out before you. It's late evening. The surface is calm, broken only by faint ripples reflecting the last trace of fading light. The horizon looks endless, but beneath it lies something far greater, far older, and far more complex than the surface could ever reveal. The ocean is not just a body of water, it's the planet's memory. Every wave that laps ashore, every current that sweeps across the deep, every grain of sediment that settles to the bottom is part of a story written over hundreds of millions of years. The Sunda Trench is one of those sentences carved into the sea floor, a long curving line of descent where the Indo-Australian plate slips beneath the Eurasian plate. That might sound like geology's version of paperwork, but what it really means is that the ground beneath the Indian Ocean is constantly moving, constantly reshaping the face of the Earth. Not in minutes or hours, not even in lifetimes, but across epochs. The trench itself stretches for more than 3,000 kilometres from just west of Sumatra down toward the island of Java and beyond. It's one of the deepest places on the planet, reaching almost 7,200 metres below sea level. At that depth, sunlight is a distant rumour, and the pressure is more than 1,000 times what you feel at the surface. Yet somehow in that hostile darkness, life endures. But before we sink that far, it's worth remembering how the ocean itself feels at its edge. The Indian Ocean, from which the Sunda Trench takes its breath, has always been a place of crossings. Trade winds, ancient migrations, drifting plankton, and tectonic plates all meet there. The currents that circle through it carry stories from Africa, Arabia, India, and the islands of Indonesia. Every molecule of water has travelled unimaginable distances, carrying salt, heat, and the silent traces of the planet's chemistry. The trench lies where all that motion meets resistance, where the energy of the ocean collides with the slow grind of the Earth. It's strange to think of something as heavy and immovable as a tectonic plate moving, but that's exactly what it does. Beneath the floor of the ocean, these immense slabs of rock slide past each other at the speed your fingernails grow. That doesn't sound impressive, but multiplied across thousands of kilometres, that slow crawl creates mountains, islands, and deep ocean trenches. The Sunda Trench is one of the clearest reminders that our planet is alive in its own quiet way. It bends, stretches, and folds under forces we rarely think about. And in that hidden motion lies a story not just of geology, but of everything that lives above it. If we were to follow the line of the trench on a map, it would look almost gentle, like a sweeping arc tracing the western edge of Indonesia. But what that curve represents is violent and continuous, the subduction of one tectonic plate beneath another. The Indo-Australian plate pushes northward, and as it does, it slides beneath the Sunda plate, forcing the seafloor downward and lifting the islands of Sumatra and Java upward. That collision is the reason for Indonesia's volcanoes, earthquakes, and fertile soils. It's why the region is both breathtakingly beautiful and dangerously unstable. Beneath the calm surface of the sea, immense slabs of the planet are grinding together, storing energy that sometimes releases in an instant, reshaping coastlines and altering human lives. Still, despite all that motion, the trench is not chaos. It's a structured place, a boundary where the laws of physics and chemistry are written into stone and sediment. If you could stand there, which of course you couldn't without being instantly crushed, you would see layers of rock curving downward into the abyss, the remnants of ancient ocean floors slowly melting as they sink into the mantle. It's as if the Earth has a recycling system, swallowing its old crust to make room for the new. The material that disappears into the trench doesn't vanish forever. Deep below, it melts, mixes, and eventually rises again through volcanic arcs, building new islands from the same elements that once lay buried under miles of ocean. This cycle has been happening for hundreds of millions of years, long before humans ever named the place or charted its coordinates. If the planet had a pulse, this slow subduction would be part of it, steady, relentless, and vital. When we speak of ancient secrets hidden in the trench, they're not just fossils or shipwrecks. They're the very processes that have shaped the continents, the unseen machinery of Earth's evolution. The Sunda Trench is both a graveyard and a birthplace, swallowing one world and giving rise to another. Somewhere above it, perhaps drifting in a research vessel or watching sonar screens flicker with data, a handful of scientists try to make sense of it all. They map the contours of the trench with sound waves, sending pulses into the deep and measuring the echoes that return. What they find is not a smooth valley, but a landscape more rugged than any mountain range on land. There are cliffs and ridges, canyons within canyons, and strange flat plains of sediment that look like frozen rivers. The topography of the deep sea is as complex as the surface of the moon, and yet we've only seen fragments of it. It's humbling to realise how much of our own planet remains unseen. We've mapped Mars more thoroughly than our own ocean floor. The Sunda Trench, vast and ancient, still holds regions that no camera has ever captured. The temperatures near the bottom hover just above freezing, and the water is so dense with pressure that it behaves almost like a solid. It's an environment so extreme that most equipment must be specially reinforced just to survive a few hours there. And yet, in that crushing stillness, something extraordinary happens. Life finds a way. The first time explorers sent deep-sea probes into trenches like this, they didn't expect to find much. The assumption was that nothing could live under such immense pressure. But the cameras that returned from the abyss told a different story. Transparent amphipods, pale snailfish, and bacterial mats clinging to rocks all revealed that the deep is not lifeless. It's simply different. The organisms there have evolved to thrive in conditions that would destroy almost anything from the surface. Their cell membranes, enzymes, and DNA are built to withstand pressures that would crush steel. To them, our world of air and sunlight would be unbearable. The existence of life down there raises questions about the limits of biology itself. If creatures can survive 7 kilometers beneath the ocean, under crushing darkness, what else might endure in the hidden corners of the planet? Could similar life forms exist beneath the icy crusts of moons like Europa or Enceladus? The Sunda Trench becomes, in that sense, not just a geological feature, but a window into the possibilities of life beyond our world. It's the Earth's own experiment in endurance. But for now, imagine the sound, or rather, the absence of it. Down there, the world is nearly silent. There are no waves, no wind, no human noise, only the slow creak of rock, the faint hiss of shifting sediment, and perhaps the movement of something small brushing against the hull of an exploratory probe. The darkness is absolute, the kind that no eyes can adapt to. It's not just the absence of light, but the absence of any reference at all. Every direction looks the same, every movement feels uncertain. In such a place, even the concept of time begins to blur. Above, the surface continues its own rhythm. Ships pass, storms roll, coastlines change. But the trench remains, steady and ancient, collecting the remnants of all that drifts down from above, the microscopic shells of plankton, the remains of fish, the occasional fragment of human history lost to the sea. Over thousands of years, these layers build up, turning into soft, fine sediment that blankets the floor. It's the planet's quiet archive, recording the slow fall of time itself. Somewhere in those sediments lie clues to climate shifts, volcanic eruptions, and even mass extinctions. Each layer a page in the deep ocean's book, unread and mostly forgotten. And yet, as we look at the Sunda Trench through our instruments, satellites and sensors, it's impossible not to feel a strange sense of connection. This isn't just an alien environment tucked away in the dark. It's part of our world, part of the same planet that gave rise to forests, cities, and the voice you're hearing now. The abyss and the surface are two faces of the same Earth, separated not by purpose, but by pressure. The trench is not a place we visit easily. Only a handful of manned submersibles have ever reached its greatest depths, and even those brief journeys are feats of engineering and endurance. The walls of those vessels must withstand pressures that could crush an aircraft carrier. Every bolt, every seal, every panel must be perfect, because down there's no margin for error. When explorers descend, they describe a strange mixture of awe and calm, a sense of being completely cut off from the world, surrounded by silence so deep it feels like a presence. To peer into the Sunda Trench is to look back through geological time. The rocks there carry the fingerprints of ancient oceans, long-vanished coastlines, and the earliest stirrings of life. Each layer that sinks beneath the Earth's surface carries traces of a world that once was. Fossilized microorganisms, mineral deposits, and isotopes that reveal how the planet's climate has shifted. Scientists who study these materials are not just learning about the trench. They're uncovering the story of Earth itself, a story written slowly, patiently, in darkness. When we talk about the secrets hidden in the Indian abyss, it's easy to imagine lost civilizations or mythical cities swallowed by the sea. But the true secrets are older and deeper. They're locked in the rocks and microbes, in the chemistry of the water, and in the constant motion of the plates beneath us. Every earthquake, every volcanic eruption, every ripple of heat from the mantle is a whisper from that hidden world. And as we continue to explore it, we're reminded of something quiet but profound, that the world beneath the waves is not separate from us. It shapes our weather, our climate, and even our sense of wonder. It's the foundation on which our continents rest. To understand the trench is to understand the pulse of the Earth itself. So, as we drift further into this story, let's keep that in mind. The ocean is not an empty void. It's alive with history, motion, and memory. Beneath the calm surface lies an entire world still unfolding, still creating, still keeping its secrets. And somewhere deep below, in the curve of the Sunda Trench, the Earth continues to breathe. The deeper you go, the less the ocean feels like water and more like a world in itself. The weight of the surface disappears, replaced by something slow, constant, and alive. If you could somehow stand still in that darkness and listen, you might sense a rhythm that doesn't belong to waves or currents, but to the planet itself. That pulse, faint and patient, is the Earth breathing underwater. It moves through the crust, through the mantle, through layers of stone and molten heat that have been shifting for longer than life has existed. The Sunda Trench is one of the places where that breath escapes, a narrow wound in the ocean floor where the planet exhales its secrets. When scientists talk about subduction, it can sound like a dry mechanical process, one plate sliding beneath another. But in truth, it's closer to respiration. The planet consumes its old skin and forms new crust elsewhere. At spreading ridges, molten rock rises and cools to create new sea floor. At trenches like the Sunda, that old crust sinks back into the mantle, carrying with it everything that has settled there. Ancient sediments, oceanic fossils, even the chemistry of long-forgotten seas. In time, that material will melt, mix, and re-emerge as volcanic rock thousands of kilometers away. The Earth is, quite literally, recycling itself in slow motion. The Sunda Trench lies where two great plates of the lithosphere meet in a collision that never ends. On one side, the Indo-Australian plate moves northward, a vast raft of oceanic crust and continental fragments sliding beneath the edge of the Sunda Plate, which forms the base of Indonesia and parts of Southeast Asia. The line between them is not smooth. It's a jagged, twisting frontier of faults and fractures, each one capable of storing immense energy. Over centuries, that energy builds until it releases suddenly, shaking the sea floor and everything above it. It's that same motion that has built Indonesia's volcanic arc, the long chain of islands that rise like stepping stones between the Indian and Pacific Oceans. Imagine the scale of this system. The plates themselves are tens of kilometers thick and thousands of kilometers wide. The boundary between them descends at an angle, plunging from the ocean floor down toward the mantle over hundreds of kilometers. The rocks at the top are cold, brittle, and fractured, while deeper down they soften and deform under heat and pressure. As the subducting plate sinks, water trapped in its minerals is released into the overlying mantle, lowering its melting point and creating pockets of magma. That magma rises through the crust, feeding volcanoes like Krakatoa, Tambora, and Mount Merapi, names that have shaped both the geography and the mythology of Southeast Asia. But even knowing all of this, the reality of it is hard to grasp. These movements happen on scales of time so vast that they stretch the imagination. A few centimeters a year may not sound like much, but over 1 million years it's the difference between continents colliding or drifting apart. The Sunda Trench is the visible edge of that slow collision, the place where the invisible machinery of the planet brushes up against the world we know. At the surface, life continues almost unaware. Fishing boats glide above waters that look ordinary. The sky changes, storms come and go, and people go about their lives along coastlines shaped by this hidden motion. Beneath them, however, the crust is folding and sinking, slipping and catching. When it locks, pressure builds. When it breaks, the sea itself rises in response. It's difficult to comprehend that what happens 10 kilometers below the seafloor can send waves racing across oceans. But the Indian Ocean has learned that lesson more than once. Still, between those dramatic moments of release, the system breathes quietly. The seafloor near the trench is not dead rock. It's porous, fissured, and constantly venting. Small seeps release methane and other gases. Fluids rich in minerals rise from the depths, carrying heat and chemical energy that support entire ecosystems of microbes and crustaceans. To most forms of life, such places would seem toxic. But in the darkness of the Hadal zone, where sunlight cannot reach, chemistry replaces photosynthesis. Instead of plants turning light into energy, bacteria turn chemicals into life. These microbes form the base of a food web that includes worms, amphipods, and even larger scavengers that drift in from the upper layers, feeding on whatever the deep currents bring. Every few years, new expeditions return from the trench with footage that looks otherworldly. Ghostly fish with translucent bodies, jelly-like creatures drifting in slow motion, and pale crustaceans picking their way across the sediment like careful travellers on an alien landscape. Each discovery reminds us how little we know. The pressures down there are so intense that each square inch of a creature's body must resist thousands of kilograms of force, yet they move with effortless grace. Their bones, if they have any, are fragile and minimal. Their bodies are mostly water, perfectly adapted to a place where solidity is dangerous. The Sunda Trench, like all subduction zones, also serves another purpose. It regulates the carbon cycle of the planet. As oceanic crust sinks, it carries carbon-rich sediments and carbonates from the sea floor into the mantle. There, some of it is trapped for millions of years, while some returns to the surface through volcanic emissions. It's a long, slow exchange that keeps the planet's atmosphere in balance. Without it, carbon would accumulate endlessly, or disappear completely, and the climate we depend on would collapse. The trench, in that sense, is not just a geological feature, it's part of the planet's metabolism. To see this clearly, scientists use a combination of satellites, seismographs, and ocean bottom sensors. Each earthquake, each tremor, each pulse of heat from a vent adds another clue. From space, tiny shifts in the shape of the ocean floor can be measured in millimeters. On the seabed, pressure sensors record the faint rise and fall of the crust as it flexes. Together, these instruments let us glimpse the planet's breathing pattern, slow, deep, and unending. When we say the Earth breathes underwater, we don't mean it metaphorically. There are literal exchanges of gases, fluids, and heat that pass through the crust every day. The ocean floor is laced with cracks where fluids escape, carrying with them traces of the mantle's chemistry. At some of these vents, temperatures reach hundreds of degrees Celsius, yet the surrounding water remains near freezing. The meeting of these extremes creates gradients that power strange forms of life and complex chemical reactions. Some scientists believe that life itself may have begun in places like these, at the edges of deep sea vents where minerals, heat and water combine to form the first organic molecules. If that's true, then the processes at work in the Sunda Trench today are echoes of the same forces that gave rise to every living thing on the planet. It's remarkable how easily we forget that the continents are temporary. Mountains rise and crumble, seas open and close, and trenches like the Sunda come and go. The Indian Ocean itself is relatively young in geological terms, only about 100 million years old. Before it existed, the land masses of India, Australia, and Antarctica were part of a single supercontinent. When they broke apart, the ocean began to form, and with it the first traces of the trench. The movement continues today, slowly changing the map of the world beneath the surface of the waves. Even now, the Indo-Australian plate is not a single, solid block. It's fracturing, splitting into smaller sections that move at slightly different speeds. Those subtle differences add complexity to the region's seismic behaviour, making it one of the most active and unpredictable on Earth. The Sunda Trench is at the centre of that tension, absorbing the strain and occasionally releasing it with devastating force. Every major earthquake there is a reminder that the boundary between calm and chaos is razor thin. Yet there's beauty in this motion. The same processes that cause destruction also create the landscapes that sustain life. The volcanic arcs above the trench build fertile soils that support millions of people. The upwelling currents that rise along the subduction zone bring nutrients from the deep to the surface, feeding plankton, fish, and the vast food webs of the Indian Ocean. Even the sediment that falls into the trench carries traces of life from above, slowly transforming into rock that will one day rise again. Every breath the earth takes under the sea nourishes the world above it. From time to time, research vessels lower instruments into the depths, sometimes attached to long cables, sometimes carried by free-falling landers. These machines descend through layers of increasing pressure, their lights cutting narrow beams into the black. For hours they drift downward, recording temperature, salinity, and chemical composition. When they finally reach the seafloor, they often find a world that defies expectations, not barren, but teeming with small, resilient forms of life. In recent years, scientists have even discovered plastic fibres and industrial chemicals in samples taken from the deepest sediments. It's a sobering reminder that even the most remote places on Earth are no longer untouched. The planet breathes deeply, but it also carries the traces of our presence in every layer. Still, the trench holds more than warnings, it holds possibility. The microorganisms that live in its extreme conditions have evolved enzymes and biochemical pathways unlike anything found at the surface. Studying them could reveal new medicines, new materials, or entirely new ways of understanding biology. Some of these microbes can metabolize methane, others can survive in near-toxic levels of heavy metals. Their existence expands our understanding of what life can be. To them, the trench is not a prison, but home. Above the subduction zone, volcanoes rise like punctuation marks on the surface, each one fueled by the slow movement of the plates below. Their eruptions, though often destructive, are part of the same system that drives the trench. When Mount Tambora erupted in 1815, it threw so much ash into the atmosphere that global temperatures dropped for more than a year. That event, known as the Year Without a Summer, led to crop failures and famine across continents. It was a planetary echo of the processes happening in the deep: heat, pressure, and release. The same breath that moves the seafloor also shapes the sky. When you look at a globe, it's easy to see the continents and oceans as separate realms. But in reality, they are one continuous surface, folded and stretched by the same forces. The Sunda Trench is a reminder of that connection. It's not an endpoint, it's part of a loop. Material sinks there, melts, and eventually rises again somewhere else. The Earth doesn't waste or discard, it transforms. Every mountain, every island, every pebble was once part of something else. If you could speed up geological time, the planet would look like a living organism. The plates would ripple and flow like muscles. The oceans would open and close like lungs. Volcanoes would flare and fade like heartbeats. The Sunda Trench would contract and expand, swallowing old crust and exhaling new islands. From that perspective, the planet isn't static at all. It's breathing, slowly but constantly, through the rhythm of creation and destruction that defines it. Even now, in the quiet dark of the Indian Ocean, that breath continues. Sediment falls, crust bends, fluids seep, microbes metabolize, and far above, unaware of the motion beneath them, people watch sunsets along Indonesian beaches, feeling the sand between their toes, never realizing that the ground beneath them is slowly tilting toward the deep. The Earth's breath is not something we can stop or control. It's the background of existence, the slow beat that everything else follows. The Sunda Trench is one of its deepest exhalations, a reminder that even the most stable-looking landscapes are moving, bending, and changing. In that sense, the abyss below the Indian Ocean is not just a mystery to be solved, but a connection to something vast and ongoing, the ceaseless renewal of the planet itself. And somewhere in that slow motion lies the story we'll keep following, deeper still into the ancient history of how the ocean came to be and what it remembers. When you look at a map of the world, it's easy to think of the ocean as one thing, a vast blue field wrapping around the continents. But if you peel back the surface, you begin to see that the seafloor is not smooth at all. It's a landscape of ridges, plains and deep valleys, every bit as dramatic as the mountains and deserts above water. The Sunda Trench lies along one of the most important boundaries on that map, a place where two enormous pieces of the planet meet and reshape one another. To call it a collision isn't wrong, but it's not the sudden kind we imagine from impact. It's more like two slow-moving worlds sliding past each other in the dark. They're meeting, leaving scars that stretch for thousands of kilometres. One of those worlds is the Indo-Australian Plate, an immense slab of crust that carries both continental and oceanic sections. On the other side is the Sunda Plate, a smaller but thicker section that underlies much of Southeast Asia. Where they meet, the denser oceanic crust of the Indo-Australian Plate bends downward, sinking beneath the lighter rock of the Sunda Plate. This movement happens at a rate of about 6 to 7 centimetres a year. That's roughly the speed at which your fingernails grow. But when you extend that over geological time, it adds up to immense shifts. Entire seas opening and closing, coastlines migrating, and new land rising from the depths. What makes this meeting remarkable is how completely it ties together the surface and the deep. The same movement that pulls one plate under the other drives the volcanoes of Indonesia, shapes the islands that line the Java and Sumatra coasts, and fuels earthquakes that can shake half the planet. Every few centuries, that slow glide is interrupted by sudden, violent adjustments, the kind that release stored energy built up over centuries. The 2004 Indian Ocean earthquake, which triggered one of the most devastating tsunamis in recorded history, began with a fault rupture along this very boundary. In a matter of minutes, hundreds of kilometres of seafloor shifted upward, displacing billions of tons of water. That one event reshaped entire coastlines and altered the tilt of the Earth by a fraction of a degree. Between these dramatic moments, the trench continues its slow work. The subducting plate bends downward, dragging cold, oceanic crust deep into the mantle. As it descends, it carries with it the sediments that have settled on the sea floor for millions of years, dust from distant continents, the remains of microscopic life, volcanic ash from ancient eruptions. These layers of history are compacted, heated and transformed as they sink. Water locked within the minerals escapes and rises into the overlying mantle wedge, where it lowers the melting point of the rock. The result is a steady generation of magma that feeds volcanoes on the surface. If you were to trace a line from the floor of the trench upward through the crust, you would pass through an entire vertical ecosystem of geological and biological processes. At the bottom, there's the abyssal plain, where sediment settles like snow in total darkness. Then comes the descending slab of crust, cold and rigid, moving downward at a shallow angle. Above it, a zone of intense friction where earthquakes originate, their depths marking the boundary between brittle rock and partially molten material. Higher still lies the arc of volcanic islands, each one formed from the recycled crust below. It's a full cycle of creation and destruction playing out in slow motion, connecting the ocean floor to the sky. The meeting of the Indo-Australian and Sunda plates is not a single event or line. It's a region, wide, complex and dynamic. Scientists call it a subduction zone, but that term can feel sterile compared to the reality of what happens there. Picture one plate diving beneath another, folding and grinding, the edges fracturing as they go. The pressure generates heat, but it also creates pathways. Along those faults, fluids rise and gases escape. Entire networks of venting systems crisscross the sea floor, invisible except to the instruments that measure them. They form part of the Earth's circulatory system, moving materials between the surface and the deep interior. What's extraordinary about the Sunda Trench is its age. It didn't form recently. The collision that created it began tens of millions of years ago, long before the modern configuration of continents. At that time, the Indian plate was still moving northward after breaking away from Gondwana, the ancient southern supercontinent. As it drifted, it collided first with Eurasia, giving rise to the Himalayas, and then continued to push beneath the smaller microplates to the east. The Sunda subduction zone was one of the results, a long curving frontier where the energy of that drift continues to be absorbed. The trench we see today is the latest expression of that ancient movement, still active, still reshaping the region. It's difficult to imagine the scale of what happens in that hidden boundary. The plates themselves are made of solid rock, but over vast distances and timescales, they behave like slow-moving fluids. Their motion is driven by convection currents in the mantle, a layer of semi-molten rock that circulates heat from the planet's interior to the surface. Where those currents rise, they push plates apart, creating new crust. Where they sink, they pull plates downward, recycling old crust back into the mantle. The Sunda Trench is one of the planet's main downwelling zones, a place where the Earth folds inward on itself. When researchers study the region using seismic waves, they find that the descending plate forms a slab that penetrates deep into the mantle, perhaps as far as 600 kilometres, In some places it's nearly vertical. In others, it bends gently, creating a series of deformations that appear as earthquake zones on the surface. Each tremor, large or small, is part of this vast interaction. Some release energy harmlessly into the sea. Others, when the stress is great enough, can trigger tsunamis, landslides, or volcanic eruptions. The trench is not uniform. Its shape varies along its length, curving and twisting as it follows the complex geometry of the plates. Near Sumatra, the subduction angle is shallow, creating a wide accretionary wedge where sediments are scraped off the descending plate and piled up. These sedimentary layers form ridges and faults that extend toward the islands, sometimes storing enough strain to produce major earthquakes. Farther east, near Java, the angle steepens and the trench becomes narrower, with less sediment and sharper gradients. Each segment behaves slightly differently, making it difficult to predict how the system as a whole will respond. When scientists model these interactions, they often use analog experiments, pressing together layers of sand and clay to mimic the motion of the plates. Under slow pressure, the materials deform, fold, and break along curved lines that look remarkably similar to real geological features. Watching it happen in miniature helps visualize how these massive systems work. The key difference is time. In the laboratory, the process takes minutes. In nature, it takes millions of years, but the underlying physics are the same: friction, pressure, and plastic flow. If you could travel down through the water column above the trench, you would pass through distinct layers of the ocean. The uppermost, the epipelagic zone, is bright and filled with life. Sunlight filters through, supporting plankton and schools of fish. Below that, the twilight zone grows dim and colours fade. Deeper still lies the midnight zone, where light disappears entirely and temperatures drop near freezing. By the time you reach the Hadal depths of the trench, the pressure exceeds 1,000 atmospheres, and the environment seems utterly alien. Yet even there, the geological motion continues beneath your feet. The meeting of the plates is not something abstract. It's happening directly below that silent black water, unseen but constant. Every few decades, deep-sea missions bring back new data from this boundary. One of the most revealing studies used seismic tomography, a method similar to medical CT scans but applied to the Earth. By analysing how earthquake waves travel through the planet, researchers can create 3D images of the subducting slab. What they see beneath the Sunda trench is a long, cold tongue of rock descending into the mantle. Around it, regions of partially molten material form pockets where heat accumulates. Those pockets feed the volcanic arcs above and influence the pattern of earthquakes that ripple across the region. It's an elegant, if dangerous, balance. The descending plate cools the mantle, while the rising magma warms it. The interaction maintains a kind of dynamic equilibrium. Over geologic time, this process stabilizes the planet's crust, preventing heat from building up too much in any one place. Without subduction zones like the Sunda, Earth's surface might resemble Venus, hot, stagnant, and volcanically overactive. Instead, the cycling of crust and mantle allows the planet to regulate its own internal temperature. In that sense, the meeting of the Indo-Australian and Sunda plates is not just a local phenomenon. It's part of a planetary system that keeps Earth habitable. The slow recycling of crust influences everything from atmospheric composition to ocean chemistry. When carbon-bearing sediments are subducted, some of the carbon is stored deep within the Earth, while the rest is released gradually through volcanic outgassing. This balance helps maintain the levels of carbon dioxide that control the planet's temperature. The deep ocean, the atmosphere, and the mantle are all connected through this invisible exchange. It's strange to realise that the deep sea, so far removed from daily life, has such a direct influence on the air we breathe. The gases released by volcanoes that line Indonesia's islands, the nutrients brought up by oceanic currents, even the shape of weather patterns over the Indian Ocean, all trace their origins back to the same tectonic heartbeat beneath the trench. The meeting of these two worlds, solid and fluid, drives much of what we consider natural. There's another layer to this story, one that reaches into biology. The heat and chemicals released along subduction zones provide energy for microbial communities that thrive independently of sunlight. These microbes feed on hydrogen sulfide, methane and other compounds emerging from the crust. In turn, they form the foundation of small ecosystems that include tube worms, crabs and other scavengers. For them, the meeting of the plates is not a catastrophe but a lifeline. The Earth's slow motion creates habitats where life can persist against all odds. Even in shallower waters above the subduction zone, the effects are visible. The volcanic islands formed by this process host some of the most diverse ecosystems on the planet. Ash from eruptions enriches the soil, feeding forests and crops. The minerals carried by rivers into the sea sustain coral reefs and fisheries. The same geological processes that destroy also renew. Without the subduction beneath the Sunda Trench, the region's landscape, climate and biodiversity would be entirely different. Over millions of years, the motion of these plates has shifted the position of entire continents. India, for example, began near the South Pole and has since drifted northward across the equator. As it moved, it changed the circulation of oceans and the pattern of monsoons. The continued subduction beneath the Sunda Trench ensures that this evolution isn't over. The boundary will migrate, the islands will move, and the shape of the Indian Ocean will keep changing long after we're gone. When we think of the Earth's history, we often divide it into ages of Paleozoic, Mesozoic, Cenozoic, as if they were chapters in a book. But the meeting of plates doesn't obey those divisions. It's an unbroken process, always in motion, indifferent to our labels. The rocks that sink beneath the trench today will one day rise again as mountains or islands in a different ocean. The materials that form our continents have all passed through this cycle countless times. The Earth doesn't forget, it just keeps rewriting itself. Above it all, the ocean remains both witness and participant. Its weight drives the subduction, its water infiltrates the crust, and its sediments feed the trenches. The sea and the solid earth are not separate systems, but extensions of each other. The meeting of two plates is also the meeting of two worlds, one of rock and one of water, each shaping the other in ways both subtle and profound. The Sunda Trench is one of the rare places where that connection is visible, at least in theory. It's where geology and oceanography merge into one continuous story. And as we follow it deeper, we start to realise that what we call the surface is just a thin boundary layer between the atmosphere and a vast living interior. The meeting of the Indo-Australian and Sunda plates is not just a point on a map. It's a reminder that our planet is still very much alive, still breathing, still remaking itself from the bottom up. And as we continue this descent into the Indian abyss, we begin to see that what's happening beneath those waves isn't just about motion or rock. It's about memory. The memory of oceans that no longer exist, of continents long vanished, of the deep time that shapes everything we see today. The Earth has been meeting itself in different forms for billions of years, and the Sunda Trench is just the latest conversation between its restless parts. When you trace your finger across a map of the Indian Ocean, it's hard to imagine that the blue expanse you're looking at is younger than the mountains that surround it. It looks timeless, ancient, and unchanging. But the Indian Ocean, like every part of our planet, had a beginning. And that beginning lies far beyond recorded history, far beyond even the memory of continents as we know them. To understand the Sunda Trench, you have to understand the ocean it breathes through, because the trench is not just a feature on the seafloor. It's the echo of an ocean that has been shifting, stretching, and renewing itself for over 100 million years. The story begins in a world that no longer exists. Roughly 180 million years ago, the supercontinent Gondwana covered much of the southern hemisphere. It was an enormous landmass that included what are now Africa, Antarctica, South America, Australia, India, and the Arabian Peninsula. There were no Indian or Atlantic Oceans then, just a vast global sea called Panthalassa, and a smaller one called the Tethys that lay between Gondwana and the northern supercontinent Laurasia. The world was warmer, and the dinosaurs had only recently started to dominate the land. Everything that would become the Indian Ocean was, at that time, locked within the heart of a single continental body. Slowly, heat from within the earth began to build beneath Gondwana. The mantle stirred, pushing upward through fractures in the crust. Lava rose, solidified, and cracked the supercontinent apart. What began as a fissure widened over millions of years, filling with seawater, becoming the first trace of the Indian Ocean. As the plates drifted apart, new oceanic crust formed along mid-ocean ridges, while older crust was pushed outward and eventually recycled in subduction zones like the one we now call the Sunda Trench. If you could see that ancient world in motion, it would look like a slow dance of continents. India began to drift northward, splitting away from Madagascar and moving toward the equator at surprising speed. By geological standards, almost like a runaway train. Australia lagged behind, and Antarctica stayed near the pole, covered in forests rather than ice. The ocean that opened between them grew wider, deeper, and more complex. Currents began to form, carrying heat and salt from one hemisphere to another, changing weather patterns around the globe. By about 100 million years ago, the Indian Ocean had taken shape as its own basin, bounded by Africa on one side and the drifting fragments of Southeast Asia on the other. It was an ocean still under construction. Volcanoes lined its edges. Sediments from newly formed rivers poured into it. Coral reefs began to form along its shallower shelves. In those early ages, marine life was undergoing a revolution. Fish diversified, marine reptiles thrived, and plankton species emerged that would later form the limestone cliffs of continents. Every grain of sediment that settled in the growing ocean carried with it a fragment of that evolving world. India's northward journey would eventually close the Tethys Sea and raise the Himalayas, but before that collision, it passed directly above the location that would become the Sunda Trench. As the plate moved, it dragged with it the oceanic crust that had formed along its southern margin. That crust, now dense and cool, began to sink beneath the lighter, continental crust of Eurasia. The first outlines of the trench began to appear tens of millions of years ago, marking the line where the Indian Ocean began to fold under the landmass of Southeast Asia. From that moment on, the trench became a kind of hinge, connecting the history of two oceans, the dying Tethys to the north and the rising Indian Ocean to the south. What makes this history fascinating is that it's still being written. The Indian Ocean is the youngest of the major oceans, but it holds some of the oldest geological fragments on Earth. Along its floor, hidden beneath layers of sediment, lie traces of ancient continental crust, relics of Gondwana that never fully sank. Scientists have found microcontinents like the Kerguelen Plateau, and fragments of a lost land called Mauritius buried beneath volcanic layers. These pieces tell us that the ocean we see today is built on the bones of older worlds. When we talk about the Indian Abyss, we're really talking about an ocean that remembers what came before. The ocean floor itself records that memory in layers of rock. Each layer represents a different era of the planet's evolution. Closest to the mid-ocean ridges, where new crust forms, the rocks are young, sometimes less than 10 million years old. Near the trenches, where crust is consumed, the rocks are ancient, some over 100 million years old. Between them lies a gradient of age and transformation. By studying magnetic patterns frozen in the basaltic crust, scientists can trace the history of the planet's magnetic field reversals, which act like a barcode revealing how the ocean floor has spread over time. The pattern shows that the Indian Ocean has been expanding unevenly, with ridges that have shifted direction and changed speed as the plates around them collided and rearranged. One of the most important features of the Indian Ocean is the Central Indian Ridge, a long underwater mountain range that runs from the southern tip of Africa to near the equator. It's here that new crust is created as magma wells up and solidifies, pushing the older crust outward toward the Sunda Trench and other boundaries. This slow but constant production of new seafloor is what drives subduction elsewhere. The Earth's surface area remains roughly constant, so for every kilometre of crust created at a ridge, another must sink somewhere else. The Sunda Trench is the counterbalance to that creation, the inhale to the ridge's exhale. When viewed this way, the Indian Ocean is not static but circulatory. It's part of a planetary loop in which matter, heat and energy move continuously between surface and depth. The ocean's floor is constantly being born, aged and renewed. It's a process so slow that no human lifetime could ever witness it change, and yet the results surround us. The islands, the mountains, the shifting lines of coast. The very minerals we use, the oxygen we breathe, and the climate we live in are shaped by this movement. And yet, for most of human history, the ocean's story remained invisible. Ancient civilizations along its shores, the Indus Valley, the Persians, the Arabs, the Indonesians, sailed its surface and mapped its winds, but never saw the world beneath. To them, the sea was vast and mysterious, a boundary between lands and a source of life, but not something with its own geological history. It wasn't until the 20th century, when sonar mapping and oceanography matured, that we began to see the Indian Ocean's floor in detail. What those maps revealed was astonishing. A network of ridges, fracture zones, plateaus, and trenches that mirrored the complexity of any continent. The Sunda Trench stood out immediately, a deep, narrow scar at the edge of the basin, a reminder that even as the ocean expanded, it was also being drawn back into the planet. What makes the Indian Ocean distinct among the world's seas is its asymmetry. Unlike the Pacific or Atlantic, it's bounded by land on three sides and open to the south. That shape influences how it circulates, how heat moves through it, and how it interacts with the atmosphere. Its monsoon system, the seasonal reversal of winds and currents, is one of the most powerful on Earth. For half the year, the ocean breathes northward toward Asia, bringing rain and life to billions. For the other half, it exhales southward, carrying cooler, drier air. This rhythmic exchange has shaped civilizations, agriculture and trade for thousands of years. Beneath it all, the tectonic plates continue their own, much slower rhythm, the deep heartbeat of the same system. When you consider the scale of that history, it's humbling to think that the ocean is still changing. The Indo-Australian plate continues to move north, and the process that created the Sunda Trench continues as well. In millions of years, new islands will rise, old ones will erode, and the shape of the Indian Ocean will evolve again. Some geologists even predict that the plate will eventually split completely, creating a new boundary and perhaps a new trench farther south. To the Earth, a million years is a blink. What we see as permanent and the shape of continents, the course of ocean currents, are only temporary arrangements in a long, slow sequence. This slow rearranging is not without consequence. Each shift in the ocean structure affects global climate, sea level and biodiversity. When continents move, they change how heat is distributed across the planet. The rise of the Himalayas, for example, altered global wind patterns and intensified monsoon circulation. The closure of the Tethys Sea redirected ocean currents, leading to the modern pattern of thermohaline circulation, the deep conveyor belt of warm and cold water that regulates Earth's temperature. The Sunda Trench and the subduction system it anchors are part of that chain of cause and effect. The deep movements beneath the Indian Ocean help determine the climate above it. Every grain of sand along a tropical beach, every coral reef, every seasonal storm carries within it the legacy of this ancient motion. The ocean has always been the mediator between Earth's interior and its atmosphere, transforming heat from the deep into energy that drives weather. The trench, by swallowing and recycling the ocean floor, keeps that system alive. Without subduction, the planet would stagnate. Volcanoes would eventually cease, the atmosphere would lose its renewal of gases, and the oceans would grow chemically inert. The fact that the Indian Ocean is still active, that it still breathes through the Sunda Trench, is one of the reasons Earth remains habitable. It's also why the trench holds so many unanswered questions. Every time we send instruments down into its depths, we find evidence of processes we barely understand. The sediments there are compacted records of the ocean's chemistry over millions of years. Tiny fossils of plankton and microorganisms preserved layer by layer act as a timeline of climate change. Isotopes in the minerals record shifts in temperature and carbon dioxide. By studying them, scientists can reconstruct how the planet's climate evolved, how the monsoon system developed, and how the rise of mountain ranges affected global circulation. The trench is, in many ways, the memory vault of the Indian Ocean. Some of those memories go even deeper, into the very rocks that form the oceanic crust. As the crust sinks, it undergoes metamorphism, the transformation of minerals under heat and pressure. In the process, it releases fluids rich in elements like carbon, sulfur, and nitrogen, which then interact with the overlying mantle. These chemical exchanges have been occurring since the first oceans formed. They're part of the geochemical cycles that control the composition of the atmosphere and the oceans themselves. The air you're breathing right now, the balance of oxygen and carbon dioxide that makes life possible, is indirectly maintained by these processes happening thousands of kilometers away and thousands of meters below the surface. Even the biological history of the Indian Ocean is tied to its geological evolution. As the continents drifted apart and rejoined, species were carried with them. Some became isolated and evolved independently, others spread across new environments created by changing coastlines. The currents of the Indian Ocean acted as both barriers and bridges, guiding migrations and shaping biodiversity. The trench, though seemingly empty, forms part of that network, a silent corridor where nutrients and organic matter sink, feeding life in the deep and eventually recycling back into the surface through volcanic and tectonic activity. If we could compress the ocean's entire history into a single day, human civilization would appear only in the last few seconds before midnight. The trench would still be deepening. Volcanoes would still be erupting. Currents would still be circulating heat. From the planet's perspective, nothing has slowed. The Indian Ocean, older than memory, continues its work as though unaware of the brief species that has begun mapping it. And so the question remains, what secrets does it still hold? The answer lies not just in what we can measure, but in what we can't yet reach. Beneath the trench, beyond the limits of our current technology, the subducted slab may carry remnants of ancient crust, perhaps even traces of water or carbon that have been trapped since the earliest oceans formed. Those elements could hold clues about how the planet first became habitable. Some scientists think that the deep subduction zones act as filters, cycling water and carbon between the surface and the mantle in a balance that has kept the ocean stable for billions of years. Without that stability, life might never have survived. So when we look at the Sunda Trench today, we're not just looking at a feature of the modern world, we're looking at the visible edge of an oceanic story that began before mammals, before flowers, before the continents took their current shapes. It's a story written in basalt and sediment, in microscopic shells and shifting plates. It's the record of an ocean that remembers everything, from the heat of the Earth's birth to the faint echoes of the creatures that first swam in its depths. The Indian Ocean is not simply water, it's time made visible. And as we move deeper into its story, we start to sense that what lies beneath those miles of water isn't just geology, it's continuity. The unbroken conversation between Earth's interior and its surface, between the past and the present, between what we know and what still waits in the dark. The ocean may have been born from the breakup of a supercontinent, but what it created was far more enduring, a living, breathing system that still shapes the world around us. Somewhere far below, the Sunda Trench continues its slow descent into darkness, taking with it the memory of this ocean, one layer at a time. When light finally disappears and pressure takes its place, the ocean becomes something else entirely. Above, It was a moving mirror, bright and shifting. But below a few thousand meters, there is no shimmer, no reflection. The surface world ends somewhere around the point where the last colour fades, and all that remains is weight, cold, and silence. This is the true depth of the Indian Ocean, where the Sunda Trench cuts a path into the planet's crust, and the water presses down with the force of mountains. If the ocean's upper layers are its face, this is its skeleton, unseen, unmoving, but holding everything above in place. Down here, the word pressure barely begins to describe the conditions. Every 10 meters you descend adds another atmosphere of force. At the deepest point of the Sunda Trench, more than 7,000 meters below the surface, the pressure exceeds 700 times that at sea level. That's like placing the weight of an entire car on your thumbnail. It's enough to crush most materials into fragments. Metals deform, air disappears. Even light itself seems to stop, absorbed completely by the dense layers above. The only movement comes from the slow drift of sediment and the occasional flash of something alive passing through the cone of a submersible's lamp. The water temperature hovers just above freezing, around 2 degrees Celsius. There are no currents here in the way we think of them at the surface, only sluggish flows driven by differences in density and salinity. Every particle that falls from the surface takes weeks or months to reach this far down, and when it finally settles, it becomes part of a slow, steady snowfall of organic material called marine snow. It's made up of dead plankton, fecal pellets, and tiny fragments of detritus, drifting endlessly downward. Each flake is a small piece of the living world above, carrying nutrients to the deep. Over centuries, these particles build up into layers of soft, fine sediment that blanket the trench floor. To an outside observer, it might seem lifeless. But the truth is, even here, in this immense stillness the ocean breathes, the chemical processes that take place in these sediments recycle carbon, nitrogen, and sulfur. Bacteria thrive on the microscopic remnants of life, transforming them into gases and compounds that will eventually return to the surface through vents or subduction. It's a slow metabolism, the planet's own deep respiration. Every inch of sediment on the trench floor is alive with microbial activity, so slow and faint that it might take decades to consume a single flake of organic matter. The seafloor itself is a landscape that defies easy comparison. Sonar mapping has shown that it's not flat but rugged, filled with ridges, valleys, and steep walls where the descending plate bends and cracks. Some of these walls rise more than a kilometre from the bottom, forming what look like cliffs carved by pressure rather than weather. There are also slump zones, areas where sediments have slid down from the upper slopes, creating chaotic piles of debris. In places the seafloor ripples like fabric, warped by the constant tension between the two plates. The water here is so dense that even sound travels differently, moving faster and farther than it does above. When an earthquake happens miles away, the vibrations reach the trench like distant thunder, rolling through the deep layers of rock and water. When research teams send remotely operated vehicles down into the trench, they often describe a feeling of disconnection, not just from the surface but from time itself. The descent can take hours, during which the light fades in stages, then vanishes. The only illumination comes from the submersible's lamps, revealing small circles of the world around it. Dust and particles drift by like snowflakes, disturbed by the machine's movement. The cameras capture an alien landscape. Grey mud plains, jagged outcrops, and the occasional glint of metal or mineral. It's difficult to comprehend that this environment, hostile and silent, is part of the same planet as the warm, sunlit world above. In these depths, creatures that seem impossible manage to survive. Some are transparent, almost invisible against the black background. Others are pale and soft, their bodies adapted to the immense pressure. The Haddle snailfish, for instance, lives at depths greater than 7,000 meters. Its body has no swim bladder, which would collapse under such pressure. Instead, It maintains buoyancy through a delicate balance of fats and fluids. Its bones are thin, almost gelatinous, and its muscles contain special compounds that prevent proteins from breaking down. It moves slowly, conserving energy, feeding on amphipods and other small crustaceans that scavenge the trench floor. Those amphipods, no larger than a fingernail, are themselves marvels of adaptation. Their exoskeletons contain aluminum extracted from the water around them, which may help protect them from the effects of pressure. They feed on the organic debris that falls from the upper ocean, recycling the remains of plankton, fish, and jellyfish. Every so often, a larger carcass, perhaps a whale or shark, sinks into the trench, becoming a feast that can sustain entire communities for years. These whale falls are rare events, but they transform the deep sea when they occur, creating temporary oases of life amid the barren mud. What's remarkable about these ecosystems is that they function entirely without sunlight. Instead of photosynthesis, they rely on chemosynthesis, the use of chemical energy derived from reactions between seawater and minerals. Microbes living in or near hydrothermal vents oxidize compounds like hydrogen sulfide and methane, producing organic matter that forms the base of the food web. Even in areas without vents, chemical gradients within the sediment provide enough energy for life to persist. It's a reminder that biology can adapt to almost any conditions given time. The trench walls are sometimes punctuated by small seeps, places where fluids escape from the subducting plate below. These fluids carry with them minerals and gases released as the descending crust heats up and dehydrates. The chemistry of these seeps can be extraordinary, containing high concentrations of methane, ammonia, and other reduced compounds. Some are warm, others cold, but all create unique habitats for microorganisms. The fluids rise slowly, forming shimmering layers that distort the water above them. They are, in a sense, the exhalations of the Earth itself, the literal breath of the subduction process. There's an irony in the fact that some of the planet's most dynamic geological processes happen in its quietest places. The deep trenches are the front lines of creation and destruction, but they appear utterly still. The pressure suppresses almost all motion. There are no waves, no tides that reach this far, only the slow creep of the plates and the occasional tremor that shakes the sediment. To the instruments that record them, these tremors appear as faint blips, signals that last seconds but may represent shifts of enormous scale. Over time, those small shifts accumulate, releasing energy that can reshape the seafloor or generate tsunamis that travel across oceans. Yet between those moments, the trench remains motionless, as if holding its breath. For scientists, studying this environment is as much an engineering challenge as a scientific one. The pressure and cold destroy equipment that isn't perfectly designed. Cameras must be housed in thick titanium spheres. Lights must withstand crushing forces. Even then, failures are common. Cables snap, lenses crack, seals leak. Each expedition into the trench is an exercise in patience, with long hours spent waiting for instruments to return from the depths. When they do, the data they bring back is often limited but invaluable. Temperature readings, chemical compositions, short video clips showing flashes of movement. Each piece adds to the picture of what the deep Indian Ocean really looks like. What emerges from all this research is an understanding of the deep sea as a system rather than a void. The trench is not an isolated depression. It's connected to the entire ocean through currents, chemistry, and biology. The organic matter that drifts into it was once part of surface ecosystems. The minerals that rise from it feed volcanoes and influence the composition of seawater. Even the bacteria that live in its sediments may send spores upward, carried by plumes of water into the mid-ocean layers. The boundaries between deep and shallow, between living and inert, are far less clear than they seem. It's difficult to imagine any creature calling this environment home, but some do more than survive. They thrive. Certain species of amphipods in the Sunda Trench grow larger than their shallow water relatives, a phenomenon known as deep-sea gigantism. The reason isn't entirely clear. It may be related to the cold temperatures, which slow metabolism, or to the high pressure, which allows for more efficient energy use. In the deep, where food is scarce, every adaptation counts. Then there are the microbial mats, thin films of bacteria that cover rocks and sediments near chemical seeps. To the naked eye, they look like patches of pale dust or slime. But under a microscope, they reveal entire colonies, structured and coordinated, feeding on the gases that escape from the crust. Some of these bacteria can metabolize methane directly, turning it into organic carbon. Others form symbiotic relationships with small invertebrates, exchanging nutrients in a delicate balance. Together, they create miniature ecosystems that operate completely independently of sunlight. These organisms also play an important role in regulating the planet's chemistry. By consuming methane and other greenhouse gases before they reach the ocean surface, they act as a biological filter, reducing emissions that could otherwise enter the atmosphere. In that sense, even the smallest life forms in the trench contribute to the stability of the planet's climate. It's a quiet, invisible service, carried out in total darkness. The trench is also a place of sound, though not the kind we're used to. Hydrophones placed along the seafloor have recorded a range of noises, distant earthquakes, the rumble of submarine landslides, and even the low-frequency calls of whales passing thousands of meters above. Some of these sounds travel for hundreds of kilometers, bending and refracting through the dense water layers. When played back, they resemble a mixture of thunder and heartbeat, slow and resonant. Listening to them is like hearing the ocean's interior speak. Every once in a while, something unexpected shows up in the recordings, a metallic click, a rhythmic pulse, or a faint hum. Most of these turn out to be natural, caused by shifting rocks or gas bubbles escaping from the sediment. But they remind us how little we know. The deep ocean is still largely unmapped, and the Sunda Trench, though studied for decades, remains one of its least explored regions. Less than a handful of human missions have ever visited it directly, and even those only for a few hours at a time. The rest of our knowledge comes from machines and models. Despite that distance, the trench connects us to a reality we rarely consider, that the world beneath us is active, immense, and alive. The pressure and darkness here are not just obstacles but essential parts of the Earth's balance. They shape how the crust moves, how the oceans circulate, how life adapts. If you could somehow remove the ocean and expose the trench to open air, it would dwarf the Grand Canyon. Its walls would rise in silence, sculpted not by wind or rain, but by the invisible hand of time and gravity. And yet there's something comforting in that stillness. The trench doesn't change quickly, doesn't rush or compete. It simply exists, performing its function without witness. It absorbs, transforms, and endures. In a world where everything at the surface feels fast and temporary, the deep ocean reminds us of scales beyond our own. Here, minutes are meaningless, centuries are the units of motion. The cathedrals of pressure and darkness stand not as monuments to death, but as structures of persistence, steady, unbroken, quietly holding the memory of the planet's movements. Far above, the ocean continues to shimmer and breathe, unaware of the depths that sustain it. And below, in the silent world of the Sunda Trench, the Earth continues its slow work, recycling crust, nurturing life, and keeping its ancient balance, one unseen heartbeat at a time. If you were to lower a camera into the deepest parts of the Sunda Trench, you'd expect to find nothing. Darkness, pressure, and cold don't sound like ingredients for life. For most of human history, scientists agreed. They believed that beyond a certain depth, perhaps 6 kilometers, there could be no movement, no metabolism, no living structure capable of surviving. And yet, when the first images came back from deep-sea landers, they showed something that defied every assumption. There were creatures down there, pale, slow and fragile looking, but alive all the same. Creatures that shouldn't exist but do. It's strange to think that the harshest environments on Earth are also among the most diverse in adaptation. Life, it seems, refuses to accept boundaries. The trench floor, where temperatures hover just above freezing and pressure would crush almost anything from the surface, is home to entire communities of organisms built around principles of survival that barely resemble what we see on land. To understand them, you have to forget sunlight, forget photosynthesis, forget even the concept of comfort. Down here, everything is redefined. The first living things ever filmed in the Sunda Trench were amphipods, small, shrimp-like crustaceans that seem almost delicate, their bodies transparent and flexible. They swim in short, erratic bursts, feeding on bits of organic matter that drift down from above. To survive under pressure that would collapse a submarine, they've evolved body structures free of trapped gases. Their internal fluids are rich in compounds that prevent proteins and membranes from folding incorrectly under compression. Instead of calcium carbonate shells, which would dissolve under high pressure, they use aluminum extracted from seawater to reinforce their exoskeletons. That aluminum acts almost like armour, giving their bodies a ghostly metallic sheen under artificial light. Not far from them drift snailfish, another deep-sea resident that has adapted in ways that seem almost impossible. Their skin is translucent, their bones reduced to flexible cartilage, their bodies soft as jelly. They don't swim quickly. Instead, they float just above the sediment, gliding in slow, careful motions, as if every calorie of energy must be spent wisely. The snailfish's body chemistry is what truly sets it apart. Its cells contain a molecule called trimethylamine N-oxide, or TMAO, which stabilizes proteins under immense pressure. The deeper the species lives, the more TMAO it produces. At shallower depths, that same molecule is responsible for the distinct smell of fish. Down here, it's a survival tool. When researchers first saw snailfish at depths of over 7,000 meters, it changed the way biology understood the limits of life. Until then, the record for vertebrate depth was thought to be much shallower. Yet there they were, not only surviving but appearing calm, unbothered, even graceful in a world where pressure alone should make life impossible. Their existence forced a re-evaluation of what evolution can accomplish, when given enough time and necessity. Even smaller organisms populate the trench, invisible to the naked eye. The sediments are packed with bacteria and archaea that thrive in total darkness. Some of these microbes feed on the organic material that rains down from above. Others extract energy from chemical reactions with the minerals around them. A few even use hydrogen and carbon dioxide to produce methane, effectively performing a deep-sea version of photosynthesis without light. These microorganisms form the base of the trench's food web. Without them, nothing larger could survive. It's easy to think of these microbes as primitive, but their biochemistry is complex. Many have enzymes that function under pressures that would destroy ordinary proteins. Some can repair DNA damage caused by the slow decay of radioactive elements in the crust. Others can enter states of near suspension, waiting for years between chemical reactions, their metabolism slowed almost to a stop. Each adaptation tells a story about patience, about endurance in conditions that make movement, growth, and reproduction painfully slow. One of the most remarkable discoveries from deep-sea research is how similar these trench microbes are to forms of life that exist in other extreme environments, from Antarctic ice cores to volcanic hot springs. That similarity has inspired scientists to consider that these organisms might represent some of the oldest forms of life on Earth, survivors from an age when the planet itself was harsh and unstable. If that's true, then the deep ocean isn't just a refuge, it's a window into our biological past. The same chemical strategies that keep these microbes alive today may have been the foundation for all life billions of years ago. The creatures of the trench are not just adapted to survive the pressure, they are shaped by it. Their soft bodies, slow metabolisms, and minimal skeletons aren't weaknesses but perfect solutions to a constant force. Life in the deep is about efficiency, reducing every unnecessary structure, avoiding waste, making survival almost effortless by design. There's no space here for excess. Energy is scarce, so every system, every behavior must justify itself. In a sense, these organisms are the purest expression of evolution's logic. Do only what you must, and do it well enough to continue. Even so, some of what's found in the deep seems beyond explanation. When autonomous landers descend into the trench, the cameras occasionally capture brief flickers of light, tiny bioluminescent signals drifting through the dark. Bioluminescence is common in the mid-water zones of the ocean, but to find it this deep was unexpected. The light is faint and blue-green, produced by chemical reactions within specialized cells. Its purpose is still unclear. It could be a form of communication, a way to lure prey, or a defense mechanism against unseen predators. Whatever the reason, it's proof that even here, in total darkness, life finds a way to create its own light. Bioluminescent bacteria are also found living symbiotically on the surfaces of other organisms. Some snailfish and amphipods carry these microbes in small patches, giving them a faint glow that might help them blend in against the dim, ambient light from above. In the absence of sunlight, evolution has repurposed chemistry into visibility. Each faint flash is both signal and adaptation, a quiet declaration of existence in a place that otherwise offers no recognition. There's a particular kind of worm discovered in Adal sediments that feeds on the microscopic remains of other organisms. It burrows through the soft mud, ingesting particles and digesting bacteria as it goes. Its body is nearly transparent, its movements slow and rhythmic. Like many deep-sea creatures, it reproduces rarely and lives for long periods. Down here, where food is unpredictable, survival isn't about competition, but conservation. Everything moves in cycles of waiting for detritus to fall, for a carcass to settle, for a chemical plume to rise. Time itself seems to stretch to match the patience of the environment. The strange thing is that despite their isolation, the creatures of the trench are connected to the surface in ways we don't fully understand. When scientists analyze their tissues, they find traces of pollutants like microplastics, PCBs, and heavy metals. These substances have traveled thousands of kilometers through the water column, becoming embedded in the food web. It's a sobering discovery, a reminder that even the most remote parts of the planet aren't beyond human influence. The amphipods that feed on marine snow are also feeding on synthetic particles that have no place in nature. The trench has become a sink not just for sediment but for the residue of modern civilization. And yet the organisms continue to adapt. Some microbes appear to metabolize these pollutants, breaking them down chemically. Others incorporate them into their structures in ways that reduce their toxicity. Evolution doesn't judge what it's given, it uses what's available. The presence of human materials in the trench is tragic, but it also reveals how flexible life can be. Even in contamination, there's adaptation. The more we learn about these creatures, the more the boundaries of biology seem to blur. It's not just that they survive under extreme pressure or cold, but that they redefine what life can be. Some of the bacteria found in trench sediments have metabolic rates so slow that their entire lifespan might span centuries. Others reproduce rapidly when nutrients appear, going from dormancy to activity in hours. There are even viruses that infect these deep microbes, forming part of a microscopic ecosystem that mirrors the complexity of the surface world. Every process that exists in sunlight also exists here, only slowed, compressed, and adapted. When samples from the trench are brought to the surface, most of these organisms don't survive. The sudden release of pressure destroys their cellular structures. That's one reason why studying them is so difficult. To keep them alive, scientists have developed high-pressure chambers that simulate the conditions of the deep. Inside these sealed environments, Cameras and microscopes observe the organisms as they move, feed and divide. What they've revealed is extraordinary. Not chaos or suffering, but calm, deliberate behaviour. These creatures don't struggle against their surroundings. They fit into them perfectly. It's also in these pressurised experiments that researchers have discovered potential benefits beyond understanding the deep sea. Enzymes from Hadal bacteria, for example, remain stable under high pressure and low temperature, making them valuable for industrial and medical applications. Compounds produced by deep-sea microbes have shown antibacterial and anti-cancer properties. The chemistry that allows them to survive under such extremes could one day help sustain human life in harsh environments, from deep space to the surfaces of other planets. But beyond their usefulness, there's a more profound realization in their existence. These are not just organisms occupying an exotic niche. They are reminders that life is not fragile but endlessly adaptable. The same principles that sustain a snailfish 7 kilometers below the surface also sustain us. Pressure, temperature, scarcity. These are just conditions to which systems adjust. The difference lies in time and tolerance. In that sense, the trench is less a boundary of life than an expansion of its definition. When you think about how these species evolved, it's important to remember that they didn't appear suddenly in the deep. Their ancestors likely lived in shallower waters, gradually adapting to greater depths over millions of years. Each generation adjusted incrementally, building tolerance molecule by molecule. What we see now, transparent fish, aluminum-shelled crustaceans, dormant microbes, are the results of slow, continuous selection. The trench didn't force life to change, it invited it to learn. There's a quiet dignity to these organisms, a kind of resilience that feels almost human in its persistence. They exist without recognition, without comfort, without light, yet they continue, unhurried and precise. In the broader picture of the planet, they represent a truth we often forget, that life's strength lies not in its dominance, but in its ability to endure. Whether on mountaintops or in trenches, in deserts or glaciers, life finds the narrow space where survival is possible and builds from there. When explorers talk about descending into the trench, they often describe an odd feeling, not fear, but awe at how self-contained it all feels. Every organism, every layer of sediment, every chemical process has its role. There's no excess, no waste. The system doesn't need the surface, yet the surface depends on it. Without these deep communities recycling carbon and filtering chemicals, the ocean's chemistry would drift out of balance. The creatures that shouldn't exist are, in fact, keeping the rest of life stable, and so the trench, far from being an isolated void, is one of the most vital parts of the planet. The amphipods, snailfish and bacteria that live there are not anomalies but essential workers in Earth's vast system. They break down what falls, transform what they touch, and feed what rises again. They are the invisible foundation of everything above. As research continues, new species keep appearing, some captured by cameras, others detected through DNA analysis of seawater samples. Each discovery pushes the known limits of biology a little further. It's no longer a question of whether life can exist under such pressure, but how far it can go. If organisms can thrive here, they might also thrive beneath the icy crusts of moons or in the subsurface oceans of distant planets. The trench becomes a model, not just of survival, but of possibility. And as we drift further along this path, deeper into the unknown layers of the Indian abyss, it becomes clear that the creatures living in the Sunda Trench are not exceptions. They are evidence that life's persistence isn't an accident. It's the rule. Even in darkness, even under crushing weight, even where there should be nothing at all, there is motion, there is metabolism, and there is endurance. Beneath the restless waters of the Indian Ocean, there are pieces of a world that once stood in sunlight. They lie buried under layers of sediment, hidden by volcanic rock, erased from maps but not from the planet's memory. When scientists study the magnetic patterns and gravity anomalies of the ocean floor around the Sunda Trench, They sometimes find traces that don't belong there, fragments of continental crust in places where only oceanic rock should exist. These are the whispers of a lost continent, a landmass that vanished long before humans ever drew borders or named seas. For most of geological history, continents have been temporary. They drift, collide, fracture, and sometimes disappear entirely beneath new oceans. The Indian Ocean, though young compared to others, carries the remains of several such worlds. The largest of them, Gondwana, once spanned half the globe. When it broke apart, pieces of it sank, some staying near the surface as islands and plateaus, others sliding slowly downward, covered by new crust. The Sunda Trench lies near the edge of this ancient puzzle, where the broken shards of Gondwana meet the active boundary of the modern Earth. Among the most intriguing of these fragments is a region known as Sundaland. Today it includes the Malay Peninsula, Borneo, Java, Sumatra, and the shallow seas that connect them. But during the last ice age, much of it was dry land. The sea levels were lower by more than 100 metres, exposing vast plains that stretched from mainland Asia almost to the islands we now think of as Indonesia. Rivers once flowed where today there is only water. Forests and grasslands covered what are now continental shelves. The Sunda Trench formed the outer edge of that ancient land, a boundary between the stable shelf and the deep abyss. As the ice melted and sea levels rose, Sundaland drowned. The lowlands were submerged, leaving only the higher ridges visible as islands. The process was gradual at first, then rapid. Within a few thousand years, entire ecosystems vanished beneath the waves. For the people who would later inhabit these regions, that transformation became myth. Many of the flood stories found across Southeast Asia may have roots in this real geological event. Beneath the calm blue of the Java Sea lie the remnants of river valleys, deltas, and coastlines that once supported early human life. Farther south, beneath the waters of the Indian Ocean, lies another fragment of the lost world, the microcontinent known as Mauritius. Scientists discovered its existence in the 2010s while studying sand grains from the beaches of Mauritius. Inside those grains were tiny crystals of zircon that dated back nearly 2 billion years, far older than the volcanic island itself. The only explanation was that the zircons came from a buried piece of continental crust, now hidden beneath layers of younger rock. Seismic studies later confirmed the presence of thicker, less dense crust beneath the region, suggesting a submerged landmass stretching from Madagascar toward India. Mauritius may have once been part of Gondwana's link between those two continents, before it was torn apart by rifting and swallowed by the Indian Ocean. What's remarkable is that these sunken fragments aren't isolated. Other hidden plateaus, like the Kerguelen Plateau and the Naturalist Plateau off Western Australia, tell similar stories. Each represents a time when parts of the Earth's crust rose above sea level, formed ecosystems, and then slowly disappeared. Together, they form a record of continents in motion, of landscapes that came and went long before humans appeared. The Sunda Trench sits along the outer rim of this record, where the last remnants of those ancient structures are being recycled into the mantle. When geologists map the crustal structure around the trench, they find that the subducting Indo-Australian plate carries with it sediments and rock layers that include remnants of those old continental fragments. Some of the material being drawn downward into the Earth today once belonged to the surface of those vanished lands. It's a strange thought, that the history of lost continents is still sinking, millimetre by millimetre, into the planet's interior. The Earth is consuming its own past, not out of malice, but necessity. It's how the planet stays alive, constantly renewing itself. For a long time, the existence of lost continents was dismissed as speculation. Myths of Atlantis, Lemuria, or Mu were treated as folklore, not science. But as plate tectonics matured, evidence began to surface showing that the ocean floor isn't as simple as once believed. Not all of it is new basalt formed at spreading ridges. Some parts, especially near subduction zones like the Sunda Trench, contain older, thicker crustal blocks, remnants of continental material that have resisted complete recycling. These aren't mythical continents, but geological survivors, fragments of real land masses that were simply outlasted by the movement of the plates. Beneath the sediments near the Sunda Trench, seismic imaging reveals irregularities that could be remnants of such fragments. Patches of low-density crust, distinct from the surrounding oceanic rock, hint at deeper foundations. They're buried too far down to sample directly, but their existence is consistent with the pattern seen across the Indian Ocean, a mosaic of lost pieces fitted beneath newer layers. In some sense, the trench acts as a graveyard for ancient worlds, slowly drawing them into the mantle where they'll melt, mix and eventually return as volcanic material thousands of kilometers away. These submerged fragments also help explain why the region is so geologically active. Continental crust is thicker and more buoyant than oceanic crust, and when pieces of it are caught in a subduction zone, they distort the process. The descending plate doesn't slide smoothly beneath the overriding one. It catches, bends, and breaks. Those irregularities can create zones of intense stress, the source of many of the region's largest earthquakes. The collision between ancient continental roots and modern oceanic crust is one reason the Sunda Trench remains so dynamic and unpredictable. Beyond geology, the idea of lost continents speaks to something deeper in human curiosity. There's a sense of mystery in knowing that entire landscapes have come and gone, leaving only traces. Scientists studying these submerged regions often describe a feeling similar to archaeology, uncovering a history written not in stone carvings or artifacts, but in magnetic fields and mineral compositions. Each measurement, each core sample, adds another line to the story of a world that no longer exists above the waves. In some parts of the Indian Ocean, hydrothermal vents release fluids that carry chemical signatures from the subducted crust below. Those signatures include elements that originated in continental rocks, traces of granite, quartz, and feldspar. It's as if the Earth is exhaling the memory of the land it swallowed. When those fluids cool, they form mineral deposits that sometimes include rare metals and sulfides. Over time, they build structures that resemble chimneys or towers, rising from the seafloor like monuments to what has been lost. Studying these processes helps scientists reconstruct the evolution of the region. By comparing the isotopic composition of rocks and sediments, they can determine where the material came from and how long it's been cycling through the planet's systems. Some of the elements found near the Sunda Trench may have originated in Gondwanan rocks that once stood high above sea level. Their journey through the mantle, from mountain to magma to mineral vent, may have taken hundreds of millions of years. The Earth doesn't erase its history, it rewrites it in new forms. Even the biological world carries echoes of these vanished lands. During the last glacial periods, when Sunderland was exposed, it served as a migration bridge between Asia and the islands of the Pacific. Species of plants and animals moved freely across what is now the Java Sea. When the floods came and the land disappeared, those populations became isolated, evolving separately into the diverse ecosystems we see today. The orangutans of Borneo and Sumatra, the tigers that once roamed Java, the countless bird and amphibian species of the region, all are living descendants of that lost continent. The trench, by marking the edge of that ancient world, also marks the line between past and present evolution. There's also the question of what remains buried beneath those drowned plains. Modern sonar mapping has revealed river channels, terraces, and possible settlement sites now submerged under shallow waters. Archaeologists have begun to explore these areas, hoping to find evidence of early human migration routes. It's possible that the first people to cross from mainland Asia into the Indonesian archipelago walked across land that no longer exists. For them, the rising seas would have been a gradual but unstoppable transformation, a world shrinking year by year as the shoreline advanced inland. The myths that speak of great floods, disappearing lands and sinking islands may be distant memories of those events passed down through generations. The lost continents of the Indian Ocean, then, are not only geological curiosities, but also cultural ones. They connect physical history with human memory. Every legend of a vanished world beneath the sea may contain a kernel of truth, a recollection of a time when the map of the earth looked very different. The Sunda Trench, with its immense depth and constant motion, is the boundary where those memories sink into the geological record. What's remarkable is that even as these fragments vanish, they continue to shape the planet. When pieces of continental crust are subducted, they carry with them minerals rich in water and carbon dioxide. As these materials descend into the mantle, they release fluids that contribute to melting and magma formation. That, in turn, fuels the volcanoes that build new land at the surface. In this way, the disappearance of one continent helps give birth to another. The Earth's history is a cycle of loss and renewal. Nothing truly ends. It transforms. Some scientists speculate that the deep subduction zones beneath regions like the Sunda Trench could still contain pockets of ancient crust that have resisted melting. These could be the last physical remnants of Gondwana's buried roots. Using seismic tomography, they've detected structures in the mantle that may represent slabs of crust that sank hundreds of millions of years ago and remain suspended deep within the earth. If those slabs were ever brought back to the surface through volcanic activity, they would carry chemical signatures from a world long gone. It's an eerie thought that the rocks forming new islands today might contain atoms that once belonged to mountains that disappeared before mammals even existed. The lost continents beneath the Indian Ocean remind us that the planet's surface is only temporary. Every continent we stand on now will eventually change, fracture, and perhaps vanish beneath new seas. The landscapes we think of as permanent are, in reality, just brief arrangements of rock and time. The Sunda Trench is part of that long conversation, the point where the Earth quietly gathers its past and turns it into its future. And as we follow that process deeper, the story becomes less about what has been lost and more about what those losses reveal. The vanished lands beneath the Indian Ocean tell us that the planet remembers everything, even when it hides its memories far below. What we call disappearance is, in truth, preservation, a different form of existence, buried under pressure, waiting for the slow machinery of the earth to bring it back again. Somewhere beneath the layers of sediment, under kilometres of rock and water, the traces of those lost continents still rest, not silent, not forgotten, but continuing their journey into the deep, carried slowly toward the trench where all things return. Every so often, the calm of the Indian Ocean is broken by something that reminds the planet how alive it really is. For years, the trench sleeps in silence, its slow motion hidden beneath layers of sediment and water. Then, in a matter of seconds, it shifts. The pressure that has built quietly for centuries releases all at once, and the ocean moves. It doesn't move like a wave you can see at the beach. It moves as an entire body, rising and falling by meters across hundreds of kilometers. When that happens, the line between stability and catastrophe becomes very thin. The Sunda Trench is one of the most seismically active regions on Earth. It marks the boundary between plates that are constantly pushing, locking, and breaking free. Every day, small tremors ripple through the crust, most of them too faint to notice. They're the sound of the earth adjusting, of stress being released in increments. But sometimes the plates don't move evenly. They jam, building tension until the rocks can no longer bear the strain. When that limit is reached, the fault ruptures. In that moment, centuries of energy are released in an instant. The result is an earthquake, often followed by something even more powerful, a tsunami. On December 26, 2004, the world saw what that process can do. Off the coast of Sumatra, deep along the boundary of the Sunda Trench, the seafloor shifted upward by several meters. The rupture stretched for more than 200 kilometers, one of the largest fault breaks ever recorded. The energy released was equivalent to thousands of nuclear explosions. It lifted an entire column of seawater, displacing it outward in every direction. Within minutes, waves were racing across the Indian Ocean at the speed of a jet aircraft. By the time they reached the coasts of Indonesia, Thailand, Sri Lanka, and India, they had transformed into walls of water that carried everything in their path. Over 200,000 people lost their lives that day. Cities vanished. Villages were erased. The tsunami travelled as far as Africa, still powerful after crossing entire oceans. It was one of the deadliest natural disasters in modern history, and it came from the same deep process that quietly shapes the Earth's surface. For scientists, the event was both devastating and illuminating. It revealed how interconnected the planet's systems are, how a movement kilometres beneath the sea can reshape the lives of millions on land. The 2004 earthquake didn't come without warning signs. In the years before it, small quakes and subtle shifts in the region's GPS data suggested that stress was accumulating along the fault, but predicting exactly when and where a rupture will occur remains nearly impossible. The forces involved are enormous, and the friction along the plate boundary is uneven. In some areas, the plates slide smoothly, in others they stick. The result is a patchwork of locked zones that store energy unpredictably. The Sunda Trench, with its complex geometry and variations in sediment, is particularly difficult to model. After the main event, aftershocks continued for months, rearranging the stress along neighbouring segments of the fault. Each tremor was a small echo of the main rupture, part of the system's attempt to rebalance itself. In some ways, the trench behaves like a breathing organism, building tension, releasing it, and settling back into temporary calm. But for the people who live along its coasts, that rhythm is a constant background of risk. The same forces that create fertile islands and rich ecosystems also create the potential for destruction. History shows that 2004 was not unique. Major earthquakes have struck along the Sunda subduction zone for as long as records exist. In 1797, an enormous quake hit near Padang, Sumatra, generating a tsunami that flooded the coast. Another in 1833 destroyed much of western Sumatra and sent waves across the ocean. More recently, in 2010 and 2012, powerful but smaller quakes occurred in the same region. Each event is part of a long sequence of strain accumulation and release. When viewed over geological time, the pattern is continuous, almost predictable in its inevitability. But the ghosts of catastrophe are not limited to earthquakes. The same subduction that drives the trench also feeds volcanoes. Along the Indonesian arc, more than 100 active volcanoes rise above the sea, forming a curved line of peaks from Sumatra to the Banda Sea. Each one is connected to the deep processes occurring beneath the trench. As the subducting plate sinks, it releases water and carbon dioxide which lower the melting point of the mantle above. The resulting magma rises, finding its way to the surface through fractures in the crust. Sometimes it erupts quietly, forming new land. Sometimes it erupts violently, altering the course of history. Krakatoa is the name that most people know. In August 1883, the volcano between Java and Sumatra exploded with a force that shattered the island itself. The sound was heard more than 3,000 kilometers away. The eruption produced tsunamis over 40 meters high and sent ash 50 kilometers into the sky. For weeks afterward, sunsets around the world glowed red and purple from the dust suspended in the atmosphere. Global temperatures dropped by more than a degree for an entire year. All of it, every shock and every colour, began in the same deep mechanism that drives the Sunda Trench. A few decades earlier, in 1815, another eruption from Mount Tambora, farther east in Indonesia, had produced an even larger climatic effect. The ash it released blocked enough sunlight to cool the planet and caused what came to be called the year without a summer. Crops failed across continents, famine and disease spread. The chain of events that began in the molten rock beneath the Indian Ocean reached as far as Europe and North America, changing the weather, the harvests, and even art and literature of the time. When people describe the world as connected, this is what they mean. Even when the Earth is quiet, the potential remains. Beneath the calm surface of the ocean, stress is always accumulating. The trench doesn't sleep, it waits. Each small tremor, each minor shift, is part of a conversation between plates that has been going on for tens of millions of years. The ghosts of past catastrophes are written in the sediment layers, coarse sand and coral fragments deposited by ancient tsunamis, found meters below modern seafloors. Scientists dig into these deposits to reconstruct the history of past events. By measuring their age and composition, they can estimate how often the trench has produced major earthquakes. The pattern suggests that the 2004 event was not the first of its scale, and it won't be the last. What's unsettling is how easily the signs of these disasters fade. Within years, coastlines rebuild themselves, vegetation returns, coral regrows, the sea covers its scars. For the living world, recovery is inevitable, but for memory it's fragile. Human generations are short, and the intervals between catastrophic events are long. By the time another earthquake of equal magnitude strikes, most who remembered the last one will be gone. In that sense, each new disaster feels unprecedented, even though it's part of an ancient rhythm. There's a strange duality to this process. The same subduction that causes destruction also drives creation. Without it, the volcanoes that replenish the soil and build new islands wouldn't exist. The tectonic cycle is both destroyer and provider. After the 1883 eruption of Krakatoa, for example, the island was nearly obliterated. But within a few decades, a new volcanic cone began to rise from the same spot. By the 1930s, it had breached the surface, earning the name Anak Krakatau, the child of Krakatoa. Today, it continues to grow, erupting periodically, adding layers of fresh rock to the ocean's surface. The Earth doesn't mourn its losses, it simply continues the process of renewal. Still, the human cost of that renewal is immense. Indonesia sits directly atop the meeting point of several major tectonic plates, and its population lives among some of the most active volcanoes and seismic zones on Earth. Over centuries, people have learned to coexist with these forces, building cultures, religions, and architectures shaped by the rhythm of eruption and quake. Temples face mountains not just out of reverence, but as markers of respect for the power that lies beneath them. Farmers plant crops in volcanic soil, knowing that the same ground can one day bury everything in ash. To live near the Sunda Trench is to live with a constant, invisible presence, one that cannot be predicted or controlled. Scientists now monitor the region with an array of seismographs, GPS stations, and ocean-bottom sensors. These instruments record every tremor, every subtle movement of the crust. The data they provide help improve warning systems for tsunamis and volcanoes, but they can't eliminate the underlying risk. Nature's clock runs on scales too vast for human planning. We can understand the patterns, but we can't stop the next release. In the years since 2004, research on the trench has expanded rapidly. Oceanographic missions have mapped the fault zones in greater detail, revealing a complex network of fractures and bends. In some places, the subducting plate is broken into smaller segments that move independently, creating multiple points of potential rupture. Understanding how these segments interact is key to predicting where the next major quake might occur. But even with the best data, uncertainty remains. The system is too large, too variable, too slow for precise forecasts. The best humanity can do is observe and prepare. Beyond the physical destruction, the ghosts of catastrophe also exist in memory and culture. Coastal communities across the Indian Ocean still carry stories of the Great Wave. Stories passed down through generations, sometimes taking on mythic tones. In some villages there are stones or carvings that mark how far the water once reached. These memories serve as both warning and comfort, reminders that survival is possible. They connect the living to a history that the Earth continues to repeat. In a larger sense, the trench itself is a repository of those memories. Each earthquake leaves a geological trace: uplifted coral terraces, displaced sediments, scarps on the ocean floor. Together, they form a record of the planet's restless energy. When scientists drill into these layers, they find alternating bands of calm and chaos, fine-grained muds interrupted by coarse sands, the signatures of ancient tsunamis. Reading that record is like listening to the Earth's heartbeat through time, with every pulse marked by a surge of destruction followed by slow recovery. It's tempting to think of these events as tragedies, but in the context of geology, they're functions of balance. The crust must move to release the heat and pressure that build inside the planet. Without that release, the Earth's surface would buckle uncontrollably. The system of subduction, with all its violence, is what keeps the planet stable. The Sunda Trench doesn't destroy for the sake of it. It maintains equilibrium through motion. The cost of that balance is felt in human lives, but the mechanism itself is indifferent. The idea of catastrophe, then, is relative. For us, it's sudden and devastating. And for the planet, it's simply a correction, a necessary breath. The ghosts of past disasters linger not to frighten, but to remind us that we live on a moving world. Every earthquake, every eruption, every surge of the sea is part of the same story, a planet renewing itself from within. Even now, as the ocean appears calm, the pressure beneath Sumatra and Java continues to build. The seafloor flexes and warps by millimetres each year. Somewhere along the fault, the next rupture is already forming. It may not come for decades, or it may come tomorrow. When it does, the sea will rise again, carrying with it the memory of every event before. And just as the trench remembers, so do we. Through science, through stories, through the quiet act of watching, we bear witness to a cycle older than our species. The ghosts of catastrophe are not gone. They move with the plates, sleep in the sediments, and wait in the deep silence of the Sunda Trench. They are reminders of what it means to live on a breathing planet, one that creates beauty and destruction with the same steady hand, and never stops moving beneath our feet. When people look into the ocean, they often see reflection before they see depth. The surface is a mirror, bright and moving, showing sky, clouds, or the shape of a passing bird. But the deeper truth is that the mirror works both ways. Just as the sea reflects what's above, it also reflects what's within us. Our curiosity, our fear, our desire to understand what we can't see. The Sunda Trench, with its darkness and silence, holds that reflection more completely than any other place on Earth. It shows us what it means to reach into the unknown, not to find something, but to recognize the drive that makes us look in the first place. Every generation has tried to understand its world by exploring its boundaries. In the past, that meant mountains, deserts, or the edges of the map. Today, it means the deep ocean, the last true frontier of our planet. The trench represents that boundary in its purest form, a place where the familiar laws of light and sound begin to change. To descend into it is to move beyond ordinary experience into an environment where pressure becomes a physical reality you can feel through every surface, where darkness is complete, and where the line between life and geology blurs. For scientists, the decision to explore such a place isn't only about data. It's about confronting limits. Every dive, every probe sent downward is a test of what human ingenuity can build and what human patience can endure. When explorers lower a submersible into the trench, they are following a question as old as the species. How far does it go, and what happens when we reach the bottom? The answer, again and again, is both simple and vast. It keeps going, and what happens is that we change. The abyss doesn't give its secrets easily. The descent itself is long and slow, often taking hours. The world fades layer by layer. First, the colours disappear, red, then orange, then yellow. The last traces of green vanish around 200 metres down. After that, it's blue, then black. The only light comes from the vehicle itself, a narrow cone illuminating fragments of drifting particles. The sensation is not of falling, but of being swallowed. The deeper you go, the more you realise that the ocean isn't empty space. It's substance, thick and heavy, pressing in from all directions. In those hours of descent, scientists often report a strange calm. The noise of the surface disappears. There's no wind, no waves, no horizon. Inside the submersible, the hum of machinery and the occasional creak of the hull are the only sounds. Every vibration reminds you of the weight outside. Tons of water pressing against a thin shell of metal. It's a quiet that feels alive, not empty. You start to understand that silence isn't the absence of sound, but a different kind of presence, one that carries weight and temperature. When the lights finally reach the seafloor, what you see is both ordinary and astonishing. The sediment looks like dust, smooth and grey. Tiny ripples mark where currents have passed. Small creatures move slowly, leaving faint trails behind them. Sometimes a rock juts from the mud, covered in a film of microbes or mineral deposits. It's not a landscape designed to impress the eye, but it's one that humbles the mind. To know that you're looking at the lowest point of the Indian Ocean, at a place that has existed, unseen for millions of years, changes something in your understanding of scale. It's easy to think of the abyss as foreign, but the longer you watch it, the more familiar it feels. The slow drift of sediment resembles the dust that settles in a room. The patterns in the mud look like the surface of skin under magnification. The glow of bioluminescent organisms passing by the window feels like the movement of thought. Faint, fleeting, but constant. The deeper you look, the harder it becomes to separate what's outside from what's inside. The trench begins to feel less like a destination, and more like a reflection of the mind itself. Vast, mostly hidden, and full of slow, quiet processes that sustain everything above. In that sense, the abyss acts as a mirror. It shows how small we are in scale, but how large we are in curiosity. The same drive that led to the exploration of the trench is the drive that built telescopes and microscopes, that mapped the stars and decoded DNA. It's not just about discovery, it's about self-recognition. When we study the deepest parts of the ocean, we're also studying the deepest parts of ourselves, the parts that ask questions without expecting final answers. That reflection extends to the way the trench holds both beauty and destruction. The processes that create volcanoes and earthquakes are the same ones that make fertile soil and diverse ecosystems. Life and death, creation and collapse, are part of one continuous system. We see the same pattern in our own existence. Growth that comes from pressure, adaptation that follows failure. The Earth's surface changes through force just as people do. The trench, in that way, is not a symbol of chaos but of transformation. There's another, quieter kind of mirror in the trench, the way it absorbs and hides what falls into it. Every particle of dust, every fragment of dead plankton, every trace of human waste eventually sinks. The abyss takes it all, layer by layer, and turns it into something new. Over time, those layers become sediment, then rock. The process is slow, but complete. Nothing disappears, but everything changes form. The planet's deepest places are its memory banks, recording every event in material form. When scientists drill cores from the trench floor, they pull up those memories in slender cylinders of mud. Each layer tells a story. Volcanic eruptions, climate shifts, mass extinctions. The thicker the layer, the larger the event. Some layers are rich in microscopic shells, marking times when life flourished. Others are barren, showing times of scarcity. Reading them is like reading the diary of the ocean, written not in words but in chemistry. And within that record, there's always a faint trace of ourselves. In the uppermost sediments, microplastics, soot and isotopes from nuclear testing form a new geological marker, the beginning of what some call the Anthropocene, the human layer. Even in the deepest trench, our reflection is there. That discovery has forced a new kind of humility. For a long time, people believed the deep ocean was beyond our reach, immune to our influence. But the evidence says otherwise. Chemicals from agriculture, metals from industry, and plastics from consumer waste have all reached the Hadal depths. They drift slowly downward, becoming part of the marine snow that feeds the trench. What was once considered a pristine, untouched world now bears the fingerprints of civilization. The mirror of the abyss doesn't just show our curiosity, it shows our impact. Yet even that reflection carries complexity. The deep sea, for all its contamination, continues to function. Microbes are breaking down pollutants, incorporating foreign materials into natural cycles. Life doesn't reject change, it incorporates it. That's another lesson the trench offers. When faced with pressure, life doesn't stop. It adapts. The mirror shows not just the damage we cause, but the resilience that still exists. To look at the trench from the surface is to see a line on a map. To descend into it is to enter a world where time behaves differently. Minutes stretch into hours. Every movement feels heavy. It's not just the weight of the water, it's the weight of perspective. The deeper you go, the more you understand that what happens here is happening everywhere, just at different scales. The slow compression of sediments mirrors the slow build-up of experiences in a life. The sudden release of an earthquake mirrors the moments when something long suppressed finally breaks free. The patterns are the same, only the context changes. Some explorers describe a strange empathy that develops in the deep. The machines and instruments become extensions of their own senses, translating vibrations, temperature, and chemical data into something humanly comprehensible. It's as if, for a brief time, the boundary between observer and environment dissolves. You're not just studying the trench, you're part of its system. That's the truest mirror of all, not one that shows your reflection, but one that includes you in the image. It's also what makes the deep ocean a paradoxical comfort. The farther you go, the more alien it becomes, yet the more familiar it feels. The calm of the trench has a kind of permanence that's rare at the surface. Up above, everything is in motion. Storms, tides, human lives. Down here, time is measured differently. Processes unfold over millennia, almost imperceptibly. It's not lifelessness, it's longevity. The deep doesn't rush. It reminds us that change doesn't have to be visible to be real. When you think about it, the ocean's deepest point is not truly separate from us. It's connected by water, by gravity, by chemistry, by the same circulation that moves heat and salt around the planet. Every breath of air, every drop of rain, every plate of food depends indirectly on what happens below. The plankton that form the base of marine food chains depend on nutrients upwelled from the depths. The carbon that circulates through the atmosphere is regulated in part by how much sinks into the abyss. The trench is a part of us in ways we don't usually recognise. That connection also challenges the way we define exploration. When early explorers set out to map new lands, they sought to claim and name. But the trench can't be claimed. It doesn't offer resources or territory. What it offers is understanding. A chance to see how small human history is compared to planetary history. In that sense, the abyss is an equalizer. It doesn't care who you are, where you come from, or what you believe. It treats all things with the same quiet, relentless pressure. It reminds us that underneath everything, we share the same planet and depend on the same unseen systems. When modern expeditions reach the deepest point of the Sunda Trench, they often leave small markers, flags, plaques, or sensors. But those symbols don't last. Within days, they're buried by sediment or covered by bacteria. The ocean doesn't preserve our gestures, it absorbs them. And that's fitting. The abyss isn't a place for conquest, it's a place for perspective. It teaches that legacy doesn't come from leaving something behind, but from recognizing the larger process we're part of. The mirror of the trench reflects all of that. Curiosity, creation, destruction, humility, and endurance. It shows that the forces that shape the planet are the same ones that shape us. Pressure reveals structure. Darkness reveals resilience. The unknown reveals the desire to keep searching. What we see in the abyss is not just the deep ocean, it's the essence of what it means to live on an active, changing world. And as the lights from the submersible fade and the vehicle begins its long ascent back toward the surface, that understanding lingers. Above, sunlight waits. Below, the trench remains. Silent, unhurried, unchanged. The reflection it offers doesn't end when you leave. It follows you upward, into the light, into the air, into the everyday world that suddenly feels a little different. Because once you've looked into the abyss and seen it look back, not with hostility but with quiet acknowledgement, you start to recognize that it has always been there, not just at the bottom of the ocean, but at the bottom of everything that breathes and moves and wonders why. Long before people could reach the depths of the ocean, they learned how to listen to it. Sound travels farther in water than in air, faster too, carrying information that light never could. In the darkness of the deep, where sight is useless, sound becomes the language of the planet. It's how whales communicate across entire basins, how submarines navigate through blind water, how scientists detect the hidden movements of the Earth. The Sunda Trench, quiet as it seems, is full of sound. Low rumbles, distant cracks, faint vibrations from shifting rock and life moving unseen. To listen to the deep is to eavesdrop on the planet's conversations. When oceanographers lower hydrophones into the water above the trench, they record a world that most people never imagine. There are long drawn-out moans from distant earthquakes, each one lasting minutes, their echoes bending through layers of changing temperature and pressure. There are the deep calls of blue whales, rhythmic pulses that repeat in patterns like slow speech. There's the hiss of underwater landslides, the crackle of ice breaking far to the south, and the occasional metallic ping from a piece of equipment on the ocean floor. The recordings sound like static until you know what you're hearing. The constant voice of the earth, speaking in frequencies that never reach the surface. These sounds aren't random. They carry information about what's happening miles below. A single earthquake can send waves of vibration across an entire ocean basin. By measuring how those waves arrive at different sensors, scientists can map the movement of faults and even detect areas where stress is building. The trench acts as both a generator and a receiver, its shape focusing and channeling the sound of the planet's heartbeat. When a major rupture occurs, the entire ocean responds. It's not just the seafloor that moves, it's the water itself, flexing like a drumhead struck from below. Even without earthquakes, the deep ocean is alive with motion. Internal waves, invisible to the surface, roll through the water layers like slow tides, driven by differences in temperature and salinity. They carry energy and nutrients, mixing the ocean from within. The sound of these waves is low and continuous, like distant wind through trees. Above them, the clicking of small creatures forms another layer, a biological static made by shrimp, fish and other animals communicating or feeding. To the untrained ear, it's noise. To the instruments, it's a map of activity. Listening has become one of the most powerful tools for understanding the deep. Unlike light or cameras, sound can travel through thousands of kilometers of water without losing strength. That's why networks of underwater microphones, known as hydrophone arrays, are now spread across the world's oceans. Some are attached to the seafloor, others suspended in mid-water, all recording continuously. Together they create a kind of acoustic web, sensitive enough to detect not only geological events but biological movements as well. When a whale migrates through the Indian Ocean, the network hears it. When a submarine volcano erupts, the sensors capture its roar. When a fault shifts deep beneath the Sunda Trench, the sound races through the water and across continents. What makes the deep particularly fascinating is how the sounds change with depth. In the upper layers, where the water is warmer, sound travels more slowly. Below a certain point, Around 1 kilometre down, the temperature stabilises and the pressure increases. There, sound waves bend and become trapped in what scientists call the SOFAR channel, short for sound fixing and ranging. It's a natural waveguide that allows sound to travel vast distances, sometimes circling the entire globe. Many of the noises detected above the Sunda Trench originate far away, their energy carried effortlessly through this channel. It's one of the reasons the deep sea is such an effective communicator. It's physically built to transmit its own story. The idea of listening to the Earth isn't new. Seismologists have been doing it on land for over a century, translating ground vibrations into data. What's changed is that we can now extend that hearing beneath the oceans. In the Sunda region, arrays of seismometers and hydrophones work together, creating three-dimensional maps of the crust's movements. When a tremor occurs, it sends out waves that pass through rock and water at different speeds. By studying how those waves bend and reflect, scientists can build detailed images of the subducting plate, the fault zones, and even pockets of molten rock. The results show a system that is constantly in motion, with stress migrating along the trench like energy moving through a living organism. Listening has revealed details that visual observation never could. For example, before the 2004 earthquake, subtle acoustic signals hinted at fluid movement within the fault zone, tiny changes in pressure and gas release that likely preceded the rupture. After the event, hydrophones recorded the long resonant tone of the seafloor adjusting, a sound that lasted nearly an hour. It wasn't a single noise, but a series of harmonic vibrations, as if the ocean itself was ringing like a bell. Those recordings helped researchers understand how the rupture propagated and how energy dissipated through the system. They also demonstrated that even catastrophic events have structure, patterns that can be measured and understood. The ocean's voice doesn't belong only to geology, it also belongs to life. The calls of whales, dolphins, and fish form a biological soundscape that changes with season and migration. Blue whales produce calls at frequencies so low they're barely audible to humans, often below 20 Hz. These calls can travel across entire ocean basins, allowing communication between individuals thousands of kilometers apart. Some scientists believe that whale songs might also respond to the acoustic environment of the deep, shifting in pitch or timing to match the resonant frequencies of the ocean itself. In that sense, the creatures of the sea are not just using the medium, they're harmonizing with it. In recent decades, as human activity has expanded, a new kind of sound has entered the deep. Noise from ships, drilling, and sonar. These artificial signals are much louder than natural sources and can travel just as far. They interfere with the communication of marine animals and mask the subtler sounds of the planet. In the waters above the Sunda Trench, the constant hum of distant shipping routes is now a permanent feature of the background noise. Scientists studying the acoustic ecology of the region often compare the modern ocean to a crowded room, voices talking over each other, signals blending into static. The Earth is still speaking, but we have made it harder to hear. To counter this, researchers are developing quieter technologies and new ways of filtering data. Advanced algorithms can now separate human noise from natural patterns, isolating the faint signals of deep-sea events. Some teams use machine learning to detect patterns that might precede earthquakes, searching for the earliest whispers of movement along the fault. Others study the sounds of marine life to monitor ecosystem health. Each dataset adds to a growing archive of what the deep actually sounds like, not as an abstract idea, but as a real, continuous voice. One of the most haunting recordings made near the Sunda Trench came from a hydrophone placed at nearly 7,000 meters depth. For months it captured mostly silence. Faint rumbling, occasional clicks. Then, during a quiet period between monsoon seasons, it recorded a series of long rhythmic pulses unlike anything previously heard. The pattern repeated over several hours, with frequencies too low for known biological sources. Later analysis suggested it might have been the sound of a distant earthquake refracted through the trench's unique shape, the energy bouncing back and forth like an echo in a cathedral. Others speculated it could be the vibration of the subducting plate itself, releasing small bursts of stress. Whatever the cause, the recording remains one of the purest examples of the ocean's hidden acoustics, a reminder that the Earth is never truly silent. Listening also reveals the passage of time in ways that visual observation can't. The rhythm of the ocean changes with seasons, with temperature, with global events. During storms, the upper layers grow noisy, filled with the impact of raindrops and the roll of waves. During calm periods, the sound shifts to a steady background hum. Even solar activity influences it. Geomagnetic storms can affect the ionosphere and alter how sound propagates through the water. By listening continuously, scientists can detect patterns that span years or decades, linking the deep ocean to global climate cycles. What's striking is that all of this, every quake, every whale call, every drop of rain, merges into a single continuous field of sound. There's no silence, only layers. The deeper you listen, the more connections appear. The trench, far from being isolated, is part of a global symphony of vibration. The same frequencies that shake its walls can be measured on the other side of the planet. The Earth speaks in waves, and the ocean is its amplifier. Some researchers believe that by studying these patterns long enough, we might one day predict major geological events. The hope is that the Earth gives warnings before it moves, not through sight, but through sound. The challenge is learning to recognize those signals among the constant noise. It's a difficult task, but history shows that every form of listening we've developed has changed our understanding of the world. The telescope expanded our view outward, the microscope inward. The hydrophone expands it downward into the spaces we can't see but depend on completely. Listening to the deep isn't just a scientific act, it's also a philosophical one. To listen is to acknowledge that there's something beyond yourself worth hearing. It requires patience and humility, qualities that modern life often pushes aside. The ocean rewards those who wait, who let the data come slowly, who resist the urge to fill every silence. When scientists replay recordings from the trench, there's a moment of stillness before the first sound arrives. In that pause, you can almost feel the weight of the water, the distance between surface and seafloor, the scale of the system you're about to hear. Then the noise begins, low, steady, and endless. It's not music, but it has rhythm. It's not speech, but it carries meaning. Over time, that meaning becomes clearer. The deep doesn't hide knowledge. It distributes it differently. It doesn't show. It tells, in vibrations, in resonance, in the slow movement of sound through water and rock. By listening to it, we start to understand that the planet itself is alive in ways that don't require life as we know it. The crust flexes, the mantle moves, the water vibrates, each part communicating through pressure and sound. When explorers return to the surface after a deep-sea mission, they often describe a kind of after effect. The sounds of the surface, waves, wind, engines, feel louder, sharper, almost intrusive. It takes time to adjust back to the higher frequencies of daily life. Some say they miss the low hum of the deep, that background resonance that feels less like noise and more like presence. They describe it as calming, as if the Earth's slow rhythm somehow aligns with their own heartbeat. Listening to the deep changes your sense of time. It replaces urgency with continuity. In a way, we've always been listening to the deep without realizing it. The vibration of an earthquake, the rumble of distant thunder, the hiss of a shell against the ear, all are fragments of the same language. The ocean doesn't separate its voices, it combines them. The trench, with its immense depth and shape, focuses those sounds into a single tone that never stops, only varies in strength. Even when we're far from the sea, part of that vibration reaches us through the ground, through the air, through the shared medium of a living planet. The act of listening connects everything: the human ear, the machine sensor, the tectonic plate, the whale. It turns the trench from a physical location into an experience of continuity. To listen to the deep is to realize that the world doesn't need to be seen to be understood. It speaks constantly, patiently, in frequencies we are only beginning to notice. And once you hear it, you realize it has always been there, waiting for someone to pay attention. Even after decades of exploration, after countless dives, samples and maps, the Sunda Trench remains mostly unknown. The truth is that for all our instruments and models, we've barely touched it. Less than a fraction of its seafloor has been directly observed, and most of its ecosystems exist only as speculation. Every expedition returns with data that raises more questions than it answers. It's not failure, it's a reminder of scale. The deep ocean isn't hiding from us. It's simply too vast, too complex, and too slow-moving to yield its full story in human time. The trench runs for over 3,000 kilometers along the curve of Sumatra and Java, a wound in the Earth's crust deeper than the tallest mountains are high. Its slopes descend in gradients of darkness, through layers of temperature and chemistry that differ from anything on the surface. Each layer holds its own kind of life, its own rules. We've identified a few of them, catalogued some species, and measured some chemical flows. But beneath those fragments lies an entire world we still can't see. A world of organisms, minerals, and processes that may redefine what we think life and geology can do. One of the greatest mysteries involves the deep biosphere, the living layer buried within the sediments and rocks of the trench floor. Scientists have drilled into similar depths elsewhere in the world and found microbial communities thriving hundreds of meters below the seafloor. They feed on hydrogen, methane, and the slow decay of radioactive elements. They don't rely on sunlight or surface nutrients, only on the chemistry of the Earth itself. In the Sunda region, where organic material rains down constantly from the surface, and where fluids seep upward from the subducting plate, conditions for such life should be ideal. But no one has yet drilled deep enough here to know. Somewhere beneath those layers of mud and rock, there could be vast colonies of microorganisms, forming an ecosystem that dwarfs the visible one above. If confirmed, the implications would be enormous. It would mean that the boundary between biology and geology is much thinner than we assumed. The rock itself could be alive in a sense, filled with networks of microbes exchanging energy, forming a slow biological circuit that interacts with the planet's chemistry. Some researchers even suspect that these subsurface organisms influence earthquake patterns by changing the composition of fluids in fault zones. If that's true, then life is not just a passenger on the planet's surface, it's a participant in its mechanics. The trench, far from being a passive sink, might be one of the engines that regulates the Earth's balance. Another mystery lies in the materials that move through the subduction zone. As the oceanic plate sinks beneath the overriding crust, it carries with it sediments, fossils, and minerals from the surface. These materials undergo immense pressure and heat, transforming into new compounds that rise again through volcanic arcs. Among them are trace elements and isotopes that don't match known patterns, suggesting chemical reactions we haven't yet replicated in laboratories. Some of these reactions may produce entirely new minerals or even simple organic molecules. The trench could be not only a recycler of Earth's crust, but a natural chemical reactor, creating compounds that later become part of new ecosystems. This idea has led to comparisons with the origins of life itself. Some scientists believe that conditions similar to those in modern subduction zones existed on the early Earth, where heat, pressure, and water interacted deep underground to form the first complex molecules. If that's the case, the Sunda Trench might resemble one of the planet's ancient laboratories, still running its experiments millions of years later. By studying the fluids that escape from its faults and seeps, we might learn not only how life survives today, but how it began in the first place. Then there are the biological mysteries. Every expedition to the deep reveals new species. Some are tiny, almost invisible. Others are large and completely unexpected. In recent years, deep-sea cameras have captured organisms that defy existing classifications: gelatinous forms that move without visible muscles, translucent discs that pulse through the water like slow heartbeats. Many of these sightings last only seconds before the creature disappears into darkness. Samples are rare. Most are destroyed by pressure changes before they can be brought to the surface. That means our understanding of hadal biology is built mostly on glimpses, a mosaic of observations from scattered points across the ocean floor. One ongoing puzzle is how genetic material moves between these isolated populations. The trench's immense depth and pressure should create strict barriers between ecosystems. Yet DNA analysis shows surprising similarities between species found thousands of kilometers apart. Some scientists think deep currents act as corridors, carrying microscopic larvae or spores from one trench to another. Others believe that life in the Hadal zone may share common ancestry stretching back to when the oceans were smaller and continents closer together. Either way, the genetic connections suggest a hidden network of exchange beneath the global ocean, an unseen continuity that makes the deep less isolated than we imagine. There are also questions that reach beyond biology. The physical structure of the trench itself is still only partly mapped. Sonar imaging reveals ridges and depressions, but the resolution remains low compared to land-based surveys. It's possible that we're missing entire features, cliffs, vents, even collapsed sections, that could alter our understanding of how the subduction zone operates. Some models suggest that cavities within the descending plate might trap pockets of water or gas, creating zones of instability that influence earthquakes. Others predict that buried ridges from ancient crustal fragments could act as anchors, changing the way stress builds along the fault. Each of these hypotheses is plausible, but none have been confirmed. The only way to know is to send better instruments deeper for longer. Technology has advanced, but the trench still resists full observation. Pressure destroys almost everything that isn't built specifically for it. Even modern submersibles, designed with titanium and specialized synthetics, can only stay at the deepest points for limited periods. Communication signals weaken with depth, forcing reliance on pre-programmed missions. The result is that we often learn about the trench in fragments: a few minutes of footage, a handful of samples, a small data set transmitted before the connection fades. To truly understand it would require constant presence, a permanent observatory capable of surviving those conditions for years. Some researchers dream of building exactly that, a network of autonomous stations scattered along the trench floor, powered by geothermal energy, recording everything from seismic activity to microbial behavior. It's ambitious, but not impossible. The technology exists. What's missing is time and funding. Even if we could see everything, there would still be limits. Some mysteries exist not because we lack data, but because the systems are inherently complex. The trench doesn't follow human logic. Processes unfold on scales of centuries or millennia. A chemical reaction that seems trivial to us might shape the course of evolution in the deep. A small shift in fluid flow might change the stability of an entire section of crust. Understanding these processes requires patience, the kind that measures time in sediment layers rather than seconds. There are also philosophical limits. We approach the deep ocean with tools and language built for the surface, but much of what exists down there doesn't fit our categories. Terms like ecosystem, boundary, or even life itself start to blur. When you find bacteria living inside rocks, feeding on energy sources we can't easily define, the concept of biology becomes porous. The trench forces us to rethink our assumptions about what it means to be alive and what it means to interact with the environment. It challenges the separation between living and non-living, between cause and consequence. Another mystery concerns sound itself. Hydrophone recordings occasionally capture signals that remain unidentified, long, low-frequency tones that don't match known geological or biological sources. Some occur seasonally, others appear once and never again. They could be the resonance of tectonic plates, the movement of massive sediment flows, or even new forms of communication among deep-sea species, the more we listen, the more we realise that silence was never real. It was only ignorance. The deep is speaking constantly, and we are only beginning to recognise its vocabulary. Then there's the question of time, not just geological time, but biological and chemical time. Some of the organisms collected from Hadal depths show signs of incredibly slow metabolism. They reproduce rarely, grow minimally, and may live for centuries. If those estimates are correct, then entire generations of surface life can rise and fall, while a single deep-sea creature completes one life cycle. The trench becomes a living archive, its inhabitants moving through time differently than anything above. For them, change is almost imperceptible, evolution stretched into slow motion. Understanding those lifespans could offer insights into longevity, adaptation, and the limits of biological endurance. And beyond all of this, there are mysteries we don't yet have the language to describe. The deep doesn't present its secrets as puzzles to be solved, but as patterns to be recognised gradually. Sometimes the data contradict themselves. Instruments record temperatures that fluctuate in impossible ways, or chemical gradients that seem reversed. Instead of answers, we find complexity. That complexity isn't failure. It's the reality of a system that's been evolving for billions of years. The trench doesn't owe us clarity. It offers presence, a continuous reminder that understanding is always partial. One of the most humbling discoveries made during deep-sea research is how much of our own influence now rests at the bottom. Fragments of metal, plastic fibres, microbeads, and even traces of radioactive isotopes have been found in sediments thousands of meters down. They form a thin but distinct layer, a human fingerprint pressed into the geological record. Future scientists, if they exist millions of years from now, will find it and know that we were here. It's a sobering thought that our most lasting mark might not be on the land, but in the depths we barely know. The trench records everything, even our excess. Yet within that record lies another secret: resilience. Despite the contamination, life continues. Microbes adapt to digest synthetic compounds. Crustaceans incorporate metal ions into their shells. The system absorbs disruption and keeps functioning. It doesn't erase our presence, but it doesn't collapse under it either. That resilience may be the deepest secret of all. The capacity of life to endure conditions far beyond what it was designed for. It's not a form of hope, but of evidence. The Earth itself practices adaptation constantly, and the trench is one of its greatest teachers. Perhaps the biggest mystery isn't what's hidden, but why it matters to us. The deep ocean doesn't affect our daily lives directly, yet we keep reaching for it. We send machines into its darkness, build models to simulate its behaviour, and listen for sounds that may never have meaning in human terms. Maybe the reason is simple. The trench represents everything that remains outside our control. In a world increasingly defined by data and measurement, the deep remains untamed. It reminds us that there are still places where mystery survives, not because we're careless, but because reality is bigger than curiosity. Every discovery leads to another layer, and every answer expands the unknown. That's what makes the Sunda Trench both frustrating and extraordinary. It's not a problem to solve, but a dialogue to maintain. As long as the Earth moves, the trench will change. As long as we exist, we'll keep trying to understand it. And somewhere between those two movements, one geological, one human, lies the point of connection. The secrets we haven't found are not hidden out of reach. They're unfolding in their own time, waiting for us to learn how to see and hear at their pace. In the end, the deep doesn't reveal secrets. It reveals patience. It teaches that not knowing is part of understanding, that mystery isn't a void but a space where attention grows. The Sunda Trench holds more than fossils and pressure and darkness. It holds the reminder that the Earth is still alive, still speaking, still forming, and still keeping parts of itself unseen. Not to deny us, but to give us something worth reaching for again. When the ocean rests, it doesn't stop moving. Its surface may appear still, its depth silent, but every layer continues its slow circulation. Warm currents sink, cold ones rise, minerals dissolve, gases exchange. It's a rhythm too large to witness directly, but it continues always, reshaping the planet molecule by molecule. The Sunda Trench is part of that rhythm, a valve, a hinge, a deep fold in the Earth's breathing system. What happens there doesn't end at its walls. It moves outward through water, air and soil, reaching even the smallest living thing that depends on balance it helps maintain. Far above, the ocean looks calm. Light glances off the surface, forming small patterns that shift with the wind. A bird passes overhead, reflected for a moment before disappearing. Below that surface, the colours change in slow descent, fading from blue to green to grey. Sound falls away. The water thickens. Somewhere far below, beyond visibility, lies the trench, wide and uneven, a scar left by two plates meeting. Its edges are steep but not smooth, carved by landslides, covered by the fine snow of the ocean's constant shedding. In its deepest places, the pressure holds even molecules in tighter alignment. It is not emptiness but compression, not silence but structure. If the planet could dream, it would dream through places like this. The trench is not static. It changes on scales longer than memory. Its slopes shift, its walls fracture and heal, its sediments settle and rise. But these movements happen slowly, too slow to see. The Earth is thinking there in geological time, turning over its history in long, slow loops of motion. Every few thousand years, a new layer of sediment adds a line to that memory. Every earthquake marks a heartbeat. Every current that passes through carries a whisper of temperature and chemistry from one part of the planet to another. It's not romantic to say the ocean dreams. It's mechanical truth expressed through time so extended that it appears peaceful. People often speak of the ocean as if it were separate from themselves, vast, alien, unreachable. But what happens there doesn't stay there. The gases released from deep sea vents affect the atmosphere. The nutrients stirred by deep currents feed the plankton that produce most of the oxygen we breathe. Even the carbon stored in the trench sediments helps regulate climate at the surface. The deep ocean is not beneath life, it is within it. The processes that seem remote are the same ones that make survival possible on land. The trench, in all its depth and silence, is part of every breath taken anywhere above it. Over millions of years, this system has operated with precision. Water circulates, crusts move, life adjusts. Nothing remains still for long. But for the brief moment of human existence, it seems stable. That's the illusion of scale. We measure time in seasons and generations. The planet measures it in plate shifts and erosion. From the trench's perspective, we appear and vanish in an instant, like a ripple passing across its surface. It doesn't notice us, but it includes us in its process. Every action taken at the surface, every extraction, every emission, every shift in temperature, eventually reaches the deep. The dreaming ocean receives it all, not as intrusion, but as material. It integrates our presence into its chemistry, just as it integrates volcanic ash or meteoric dust. In recent years, scientists have begun to understand that the deep ocean plays a larger role in climate regulation than previously thought. It stores most of the planet's excess heat and a significant portion of its carbon dioxide. The circulation that moves this energy is slow, taking centuries to complete a single loop. But even slow systems change. Measurements show that the Indian Ocean is warming at depth, that its chemistry is shifting. The trench feels that change as increased flow, altered density, new gradients of pressure and heat. The planet's dream is being rewritten, one layer at a time. Some of those changes are visible in the smallest details, in the composition of sediments, in the distribution of microorganisms, in the behaviour of currents that pass over the trench. The microbes adapt first. Their chemistry adjusts to new conditions, altering the balance of gases they consume and release. That change moves upward through the food chain. Small crustaceans follow the shifts in nutrient flow. Larger animals alter their routes, their timing, their habits. Even the patterns of bioluminescence recorded by deep-sea cameras differ slightly from a decade ago. Each of these details is small, but together they form evidence that the dream is restless. For most of human history, the deep ocean was beyond reach, an abstraction. Maps ended where the blue began. Myths filled the space with creatures and kingdoms, explanations for what couldn't be seen. Now, as instruments descend into the trench, the mystery becomes measurable. But measurement doesn't replace wonder, it redefines it. The more we know, the more intricate the system appears. Every sample of water contains hundreds of unknown microbes. Every sound recording holds signals from sources we still can't identify. The deep ocean remains vast not because it's empty, but because it's full beyond comprehension. Sometimes, in the stillness of a research vessel drifting over the trench, the idea of scale becomes overwhelming. Scientists describe standing on deck at night, looking down at the black water, aware that beneath them lies 7 kilometers of space filled with cold and pressure and unseen life. The stars above seem closer than the bottom below. In that distance is both separation and connection, a reminder that the unknown is not always far away. It exists beneath our feet, surrounding us in the very system we rely on. Every technological advance brings us closer to understanding, but the trench always stays one step ahead. We build new sensors, and it reveals smaller fluctuations. We improve imaging, and it shows finer structures. Each discovery opens another question. It's not resistance, it's depth, revealing depth. The dreaming ocean doesn't hide intentionally. It simply operates on scales too large and small for easy observation. That persistence of mystery gives meaning to exploration itself. The search continues because the world continues to evolve faster and slower than we can follow. In a way, the trench reflects human thought itself. Beneath the visible surface of ideas lies pressure, motion, and quiet transformation. Just as sediments settle and compress into stone, experiences layer and compact into memory. Both systems hold energy that can release suddenly, changing everything in an instant. The deep ocean becomes not a metaphor but a structure, a physical example of how systems store complexity over time. To understand it is to glimpse the same processes that operate in the human mind, scaled to planetary proportion. Listening to the deep taught us that silence is full. Mapping it taught us that boundaries are temporary. Studying its creatures taught us that life adapts endlessly. Each step downward has mirrored something upward. The trench shows that the world is not fragile but dynamic, not static but balanced by movement. Its pressure is not a barrier but a condition of existence. Without it, the crust would drift unchecked, the volcanoes would stall, the circulation of nutrients would fail. The planet depends on its depths to remain whole. Even the moments of catastrophe, earthquakes, tsunamis, eruptions, fit within that pattern. They are not interruptions, but expressions of equilibrium. Energy builds, releases, and resets. In human time, it feels violent. In planetary time, it's maintenance. The trench carries those forces quietly, bearing the weight of motion that keeps the surface stable. It doesn't seek peace because it is peace, defined not by stillness, but by the balance of movement and rest. When explorers return from the deep, they often describe the experience not as discovery, but as recognition. The world beneath isn't alien, it's familiar in a different form. The colours, shapes, and rhythms feel like extensions of natural logic. Pressure replaces gravity as the primary force, but the principles remain the same: structure, adaptation, endurance. Some say it feels like looking at the inside of time, where everything continues but at a slower rhythm. The trench doesn't show the future or the past. It shows duration, existence stretched beyond comprehension. On a calm night above the Indian Ocean, the difference between surface and depth becomes almost invisible. The water blends with the sky and the horizon disappears. The sound of waves fades into a steady pulse, like a single constant exhale. Somewhere far below, the same pulse moves through the trench, transmitted as vibration through rock and water. It's the same frequency, the same rhythm, scaled by distance. The ocean and the planet share that heartbeat. Everything that lives above it is tuned to it without realizing. In that quiet, it's possible to sense the continuity, how the heat of the mantle drives the motion of plates, how that motion shapes the trenches, how those trenches influence the oceans, how those oceans feed the atmosphere, and how that atmosphere sustains life. The line of connection runs through every layer, unbroken. The dreaming ocean is that connection made visible through depth. It doesn't think, but it processes. It doesn't sleep, but it cycles. The dream is not about imagination. It's about persistence. If you were to descend into the trench and turn off every light and instrument, you'd still be surrounded by motion. The water would press, the rock would shift, the microorganisms would continue their chemistry. The planet would go on breathing through its slow circulations. The dream would continue. Nothing in that environment needs witness to function, yet our presence there adds meaning, not to the ocean, but to ourselves. It's the act of seeing, listening, and studying that allows understanding to grow. The ocean doesn't require awareness, but it offers it to those who ask. The trench has no beginning or end in human terms. It's a continuous fold, part of a system that stretches around the planet. But standing above it, or floating over it, it's hard not to feel that you're near something essential. The depth isn't empty space. It's accumulated time compacted into water and stone. Every current that passes through carries traces of everything that's ever happened. Dust from continents, ash from volcanoes, salt from ancient seas. The dreaming ocean holds those traces in constant suspension, moving them through cycles that will outlast any single species or civilization. There is comfort in that permanence. The trench doesn't change quickly, but it changes completely. Over tens of millions of years, it will shift position, close, open elsewhere. The plates will move on, and new trenches will form. The ocean will reorganize its depths, and new currents will emerge. But the process will remain. The dream will continue under new forms, repeating the same patterns of pressure, release, and renewal. What we study now is only one phase in an endless sequence. When people imagine the end of the world, they often think of silence, of stillness, of an ocean that no longer moves. But in reality, the ocean doesn't end. It transforms. The water we see now will one day become vapor, ice, or stone. The trench will close, but the memory of its movement will persist in the structure of mountains or the chemistry of air. The dream of the ocean is continuity, not conclusion. For those who stand at its edge, watching the horizon dissolve into night, the scale of it can feel overwhelming. Yet that scale is what keeps everything stable. The trench takes what falls, recycles it, and sends it back as something new. It has done this for as long as the planet has existed, and it will continue long after the current arrangements of continents are forgotten. The dreaming ocean is not the opposite of life. It is life extended to its fullest system, a body without edges, breathing through rock, water, and time. Somewhere far below, unseen, that body moves. It shifts slowly, pressing, folding, and sighing in the dark. Its breath is the movement of tides, its pulse the tremor of crust. Every life above it depends on that steady motion, and though we call it the deep, it's not beneath us in meaning. It's within, woven into every cell that once came from salt water. To understand the trench is to remember that origin. The dream continues whether we listen or not, but when we do, when we lower instruments, send lights into darkness, and bring back fragments of sound and sediment, we participate in it consciously. The trench is not an object of wonder alone, it's a function of our shared planet, a reminder that the unknown is not absence but scale. The dreaming ocean doesn't hide secrets for discovery. It keeps them as part of the world's ongoing thought, and within that thought, we are not outsiders looking in. We are one more layer of what the ocean remembers as it moves endlessly in its sleep.